The programs you write in this course have three major phases. The first phase is the input phase, where you ask the user for input from the keyboard or you read data from a file. The next phase is processing, where you manipulate the data, you do some sort of calculations, and then once you have the results, you have the output phase, which is where you display results on a screen or you write the results to a file of some sort. When I write programs, I usually like to keep these phases separate, so I do my input first, then my processing, then my output. I tend not to interleave them. Do some input, a little bit of processing, then some output, then more input, processing, and output, because that tends to be a bit confusing. In the processing phase, there are three major types of things you can do. The first one is sequence, doing things one after another. That's what you did with the robot example. You did one step, then another, then another, then another, one from the beginning to end until you were finished. Another type of thing that you do during processing is repetition. For example, with the robot, you could say, keep taking a step forward until you get to the door. So it would do the same step over and over and over again until some condition were satisfied, and that leads to the third kind of structure that you will find during processing, which is called conditional. So you could say to the robot, if you have an object if you have picked up an object, then put it down. Otherwise, turn counterclockwise. So your processing phase consists of sequence, repetition, and conditional structures. And that is the stuff that does the heart of the program, and that's surrounded by the input to get your data and the output to display the results. There are three types of errors that you can make in Python. The first type is called a syntax error. By the way, this number sign that I'm typing in the shell is a comment. That means Python should ignore it. It's just there for us humans to read. A syntax error happens when you say something that's grammatically incorrect in Python. So for example, if I try to say 34 plus times 8, that doesn't make any sense mathematically. It's just wrong on every possible level. So when I press the Enter key, the shell will respond, showing me that the star is where it got confused and says that's invalid syntax. You can have another kind of error called a runtime error. This happens when you do something that is syntactically valid, it's grammatically valid. For example, if I try to evaluate 42 divided by 0. Well, syntactically, in terms of grammar, I have two numbers and a division sign between them. But when it comes time to actually run that calculation, I get an error that says zero division error because you can't divide by 0. These two types of errors are usually pretty easy to find. Syntax error is the easiest because the compiler points them right out to you. And runtime errors because once you run the program, you see the error front and center. The third type of error is called the semantic error, which means you said something that's syntactically correct, grammatically, and it's not going to cause any errors when you run the program, but it doesn't do what you wanted it to. So for example, if I wanted to find out how many days there are approximately in 25 years, and I accidentally typed 25 plus 365, there's nothing wrong with that in terms of mathematics. I have two numbers with the plus sign. There's no runtime error because I can certainly add 25 and 365, but the number I get is nowhere near the correct answer because I've said something that is a semantic error. I didn't do the computation I intended to do. Semantic errors in general are the hardest ones to find because the compiler can't help you, the runtime system can't help you. It's only when you as a human look at the error, at the result and say, wow, this is not what I intended. In this video, we're going to talk a little about arithmetic operations in Python. Simplest are addition and subtraction. So for example, 4 plus 9 plus 12 gives me 25. If I have something like 25 minus 3 minus 7, the question is that going to go from left to right or right to left? In other words, is it going to do 25 minus 3 first and then subtract 7? Or is it going to take the 3 minus 7 first and then subtract that from 25? Let's try it and find out. And the answer is 15. So operations that are of the same priority, addition and subtraction, go strictly from left to right. We also have multiplication and division. So for example, 7 times 6 gives us 42. Now what happens if I say 7 plus 3 times 2? Which is going to happen first, the multiplication or the addition? According to the rules of arithmetic, multiplication should take priority over addition, and the same thing happens in Python. So the multiplication occurs before the addition does. Something interesting happens when we do division. Let's say I take 4 divided by 2. Notice the result is 2.0. So when I divide integers by integers, I always get a float as the result. In fact, if I did a type of 4 divided by 2, it would tell us that that is indeed a float. Floats divided by floats, let's say 7.2 divided by 0.4, come back as floats as a result. Sometimes you'll want to do division that gives you whole number division. For example, let's say I have 57 items and I want to find out how many whole dozens that is. If I just said 57 divided by 12, I'd get 4.75. But that's really 4 dozen plus 3/4 of a dozen. When I want integer division, I do 57 and put 2 slashes in a row. 57 divided by 12 as integer division gives me the 4. Well, what about the ones that are left over? That's 0.75 of a dozen. How do I get that integer back, the remainder? To get the remainder, use the percent sign operator, which is called remainder modulo or mod. And usually you'll hear me pronouncing it as mod. So 57 mod 12 is 9. So 57 items is 4 dozen with 9 items left over. The last operation I want to talk about is exponentiation. If I want to take 12 to the 3rd power, I type 12 star star, meaning to the power 3. And 12 cubed is 1728. I can have fractional exponents. So if I want the square root of 2, I say 2 to the 0.5 power, which gives me 1.4 or whatever. A word of warning here. Exponentiation is evaluated from right to left instead of left to right. If I take 2 to the 3rd squared, the question is that going to be evaluated as 2 cubed squared, which would come out to 64, or is it going to be evaluated as 2 to the 3 squared, which is 2 to the 9th, or 512? Let's try it and find out. And the answer is 512. The moral of the story is, if you want things to be evaluated in a specific order, use parentheses to group it the way you'd like. In order of priority, parentheses take priority over everything else. Next in priority is exponentiation. The next level down from that is multiplication and division operators, such as multiply, divide, integer division, and modulo. And the level below that is addition and subtraction operators, which are plus and minus. So if I say 3 plus 4 times 2 to the 3rd, the exponentiation will come first, so I'll have 8 times 4, because multiplication is next most important. So I'll have 8 times 4 is 32 plus 3 at the end, and I'll get 35 as the result. If I want it to be in some other order, I can always use parentheses to get the order I want. So if I wanted 7 squared times 2, and that whole thing to the third power, which would be 20 to the third power, I would put the parentheses this way. When in doubt, use parentheses. Don't be afraid to put in a couple of extra parentheses rather than trying to figure out, well, which one's the most important. It's not that much more time for the computer to evaluate, and your time is much more valuable than the computer's. Up till now, we've talked about 3 data types: integers, floats, and strings. Sometimes you'll need to convert among these data types. For example, you might have the number 37.9 and you just want the integer part of it. The int function does that for you. If I say int of 37.9, I get just 37. This does not round up or down, it just gets rid of the entire decimal part. So if I say int of negative 23.5, I'll end up with negative 23. Int will also convert strings to integers. If I say int of 245, the string, I get back the number 245. I can show that by saying, what's the type of int 245? It's no longer a string, it's class int. What happens if I try to convert something that isn't an integer, like the word 20 to integer? The answer, it's a runtime error. What if I try to take the integer of something that begins with an integer, but then has other stuff? Again, also a runtime error. Float will convert integers to float. If I say float 25, I get 25.0. This is not normally necessary. I don't have to say float of 25 plus 4.3 to do an addition such as this. I can say 25 plus 4.3 and the integer 25 will be promoted to float, and it'll work exactly as I need. Most of the time you'll be using float to convert strings to float. If you say float 37.4, you get the numeric value. You can do this with exponential notation as well. Float of 7e2 gives you 700.0. And as with int, if you take something that's not valid, you get a runtime error. You'll often have to go the other way. You'll need to convert a float or an int into a string. That's what the str function does. If I take string of 23.4, I get the string 23.4. That's a string, it's no longer a float. String of negative 45 gives me negative 45, and string of 7.3e4 gives me 73000.0. Again, that's a string, it is not a number. You can't treat it as a number. If I try to say string of 23.4 plus 5.2, it'll say, runtime error, you can't do that. You can't add strings to floats. Let's discuss some of the data types that you can work with in Python. For this video, I'm going to be using the print function to show you what the results are, much as the book does. The simplest data type is integers, whole numbers. So for example, if I want to use the number 4, I just put the number 4 there. If I want to find out what data type a value has, I can use the type function. What type of data is 4? It's an integer class data type. I can also have negative numbers, and those are also of class int. The next step up from integers are numbers with decimal points in them, called floating point numbers. So I can have a floating point number like 3.5, and if I want to find out what type of number 3.5 is, it turns out that's class float. Negative numbers are valid also, and you can also use exponential notation. For example, if I wanted 7,000, I could print 7,000, or I could say print 7e3, and that's a shorthand for saying 7 times 10 to the third power. So the e stands for times 10 to the, and that gives me 7,000 also. What about numbers that are less than 1? I can print them in the normal way, print 0.07. Now, is that leading to 0 necessary, or could I leave that off and just do 0.07? My mantra for this class is try it and find out. So let's print 0.07. Either it'll work or it'll give us an error message. And it turns out that it does work. I can use the exponential notation as well. I can say print 7e minus 2, 7 times 10 to the minus second, which is 0.07. What if I say something like print 7e46? Am I going to get a 7 followed by 46 zeros? Try it and find out. And the answer is for really large numbers or really small numbers, Python gives it back to me in exponential notation. The third data type that you'll be working with is strings. A string is enclosed in quote marks, so if I want to print the string, it works. I enclose it in single quotes, and it's displayed without the quotes. The quotes are simply there to tell where the string begins and ends. If I want to find out what kind of string, what kind of data type it is, I'll use the type function, and it says that it belongs to the class str, abbreviation for string. I can use double quotes as well. I can say print this works too. And so the question is, should you use single quotes or double quotes? And the book tends to use double quotes, and a lot of code I've read tends to use single quotes. So my suggestion is choose whichever one you like better and be consistent with it. Sometimes your choice will be forced. For example, how will I print the string that says it's working great? I can't put it in single quotes because then I'll have 3 single quotes altogether. This one will end that one, and this one's hanging out in the middle of nowhere. That's why you'll sometimes want to, that's why you will sometimes need to use a different set of quotes. By using double quotes, I can have a single quote internally, and everything's working great. What happens if I have a situation where I have both a double quote and a single quote together? So if I want to print out the string, Mrs. O'Brien said hello to us. I can't use single quotes because O'Brien used those up. Can't use double quotes because hello used up those. Python has a solution. I can use 3 single quotes in a row and then close that string with another 3 single quotes in a row. And then inside that string I can have either single quotes or double quotes in any combination that I like. And Mrs. O'Brien is happy, and so are we. Another advantage of the triple quotes is that you can have internal new lines. So if I wanted to write a poem, I could use triple, and this time I'll use triple double quotes. The boy stood on the burning deck, once all but he had fled. And I'll close that with 3 double quotes. And the output is displayed on 2 separate lines, just as I typed it. Let's say you want a program to calculate the Pythagorean theorem. Here's such a program in Python. The first 2 lines get the 2 sides, and the third line should calculate the hypotenuse. But when you run the program, and you enter side A as 3 and side B as 4, you get a name error. The name square root is not defined. The square root function isn't built into Python. It's in the math library. In order to use it, we must import the library by saying import math, and then say that we're using the square root function from the math library by saying math.squareroot. If you read from right to left, you can think of the dot as meaning belonging to. So math.squareroot means the square root belonging to the math library. Let's clear the shell, move it up a little bit, and run the program again. Side A is 3, side B is 4, and this time it works great. The hypotenuse is 5.0. Let's look at another program that implements the following formula. It's not particularly meaningful except as an example. Here's the program. There's a lot of math dotting going on in line 4. Python provides another form of importing that takes away the need for all the dots. Instead of saying import math, I can say from math import square root. Namely, you import a specific function or a list of functions from the math module. Once you do that, you don't have to say math dot everywhere. Square root works as though it was just another plain old Python function. And if I run this program, I can enter x as 100 and y as 50, and it gives me my result. Which one should you use? Import math or from math import square root? Ask me if I care.
Do you care?
No, I don't. There are some subtle differences in how they work, but at this point in the course it doesn't matter. Use whichever one you prefer. Now let's talk about trigonometric functions like sine, cosine, and tangent. For this part of the video, I'll go into the shell. I'll clear it out first. I'll import math, and then I'm going to take the sine of 30 degrees, which ought to come out to 1/2. But that's nowhere near 1/2. What's wrong here? What's wrong is that the trigonometric functions require their arguments in radians, not degrees. In the video description, you'll find a couple of links that explain radians in grand and glorious detail. The question now becomes, how do we convert degrees to radians? The answer is with the radians function. Let's try that. Let's try math.sine of math.radians of 30, which will convert the 30 degrees to radians, and now we come out with something that's much better. We don't get exactly 0.5 because the precision of the calculation is limited. Note that you can use the from import notation as well. I could say from math import sine, comma, radians. and then simply say sine of radians of 30 and get the same answer. As a side note, if you ever need to convert from radians back to degrees, there's a function called degrees that does that conversion. And that's what you need to know to use the higher math functions in Python. One of the most important things you can do when writing programs is to name your variables well. What does that mean? Let's say you want to take a person's age in years and convert it to an approximate age in days. You could write code like this. Y refers to 37, which might be their age, and then D refers to 365 times Y, and then print whatever's in D, and there's your answer. That works, but it's really not satisfying, because what does D stand for? In a large program, does it stand for days, deposit, debit, discount? Who knows? Just a single letter variable name is really not what we'd like. Your variable name should be descriptive. Try this on for size. Years refers to 37, days refers to 365 times years, print days. That's a lot more readable, and the intention is much more clear. Quick word of warning. Python is case sensitive when it comes to variable names. Upper and lower case are not the same. If I try this, years refers to 37, days refers to 365 times capital Y years, it'll say capital Y years is not defined. So those are two very different variable names. By convention, Python variables start with lowercase letters and consist mostly of lowercase. What happens if you have a multi-word variable name? What if I wanted to say age in years equals 37 to be even more descriptive, because there could be many uses of years in a large program? It won't let me do that because you can't have blanks in variable names. How is that problem solved? Programming languages have evolved two different ways of solving this. One of them is to make a single variable name with all the subwords being capitalized. I would write age, capital in, capital years refers to 37, and then age, capital in, capital days refers to 365 times age in years, and print age in days. This is called camel case because the mixture of upper and lower case, the up and down, resembles the humps of a camel, supposedly. Go figure. You'll find this as the convention for programs written in Java and JavaScript. For programs written in Python, the convention is to separate the subwords in a variable name with underscores. So in Python, age underscore in underscore years would refer to 37, and age underscore in underscore days is 365 times age in years, and print age in days. For this course, I do not really care which way you decide to do this. If you decide to do it with camel case, the first example, great, as long as you're consistent. If you decide to do it the way most Python programmers do, which I believe, by the way, is called snake case because it looks like the segments of a snake lined up one after another, I'm fine with that as long as, again, you're consistent throughout your programs. Moral of the story. Variable names should be descriptive. Y refers to 37, not descriptive enough. Years refers to 37, that's good. Age in years, 37, also descriptive, but please don't go overboard. Age in years as of current date of program. Please don't do something like that. When you use names that are descriptive, other people who read your program later on will thank you, and other people refers to perhaps you 6 months from now when you haven't looked at the code. Future you will thank past you for using good variable names. In this video, we're going to talk about the input function. Let's look at this program that we wrote in the print video. One thing I'll note is that I modified the program and I forgot to modify the description. Not only is it given an age in years, it is given a person's name and their age in years. It calculates the approximate age in days and gives personalized output. This more accurately reflects what the program does. And this program works. There's absolutely nothing wrong with it. If I run the program, it gives me the correct output. However, it's inflexible. Not everybody's named David, and not everybody is 64 years old. And in fact, next year, I won't be either. What we'd like is a way for the user to be able to take the program and run it and give us the information rather than having to modify the program every time they want to see new results. The way you do that is with the input function. I'm going to take this line and move it up here because when I run the program, I want to ask the person for their name first and then ask them for how old they are and then do the calculation. So instead of saying your name equals David, I'm going to use the input function. Inside the input function, I'm going to put something called a prompt. It's the question that I'm going to ask the user. What is your name? This is always going to be a string. Let's run this and see what happens. Remember what happens on line 6. Whenever I see this symbol, I have to work out the right-hand side first. So the input function is called to do its thing. The input function puts the prompt up on the screen and then waits for you to type something. I'll type David because that is my name. I'll say, David, your age in days is approximately 23,360. Let's run that program again. This time I'm going to say my name is Joe. I'll say, Joe, your age in days is approximately 23,360. Now I've personalized the name by asking the user for input. I want to run the program one more time and point something out. Notice that the cursor for input is right up next to that question mark, and that looks a little bit ugly to me. Just put in somebody's name, Nancy. Normally, I like to put a blank before the closing quote mark so that the blank will show up on the screen. When the blank shows up on the screen, it gives the cursor some breathing room between the prompt and where the user will type their input. Running it again, what's your name? Federica. So far, so good. Let's do the same thing for years. Let's make that an input. And we'll ask, how old are you? Again, I'll put the blank at the end of the prompt just to give my cursor some breathing room. Save this and run it again, and it's going to ask, what is your name? And this time I'll put in the name Martin. How old are you? And I'll say 20. Martin, your age is... Whoa, what the heck happened there? What happened there is strings. Whenever you do input, the result of the input function is always, always, always a string. When we asked, what is your name? That was a string and no problem. When we asked, how old are you? Instead of getting the number 20, we got the string 20. And that's what years referred to. On this line, when we evaluate the right-hand side, we're multiplying a string by a number, and as you may recall from a few videos back, when you multiply a string by a number, it repeats it that many times. So we got 365 replications of the string 20. That's why we have the age and days is approximately 2020202020, and no, I'm not going to read them all. How do we get around that problem? The answer is conversion to integer. The years is an integer, so what we will say is int of input of how old are you. What we have is a function calling a function, and let's go through this in detail to see what this computer's doing. When it sees line 7, it sees this symbol and says, oh, I have to figure out what the right-hand side works out to. The right-hand side, parentheses come first and function calls, so it first does the input call. The input call puts up the words, how old are you on the screen? And I typed in 20. That brings back the string 20. That part is evaluated, and now that string 20 is passed on to the int function, and I get a number 20 as the final result of the right-hand side, and years will refer to the number 20. Let's clear the shell and run this again. And let's have Martin be 20. And now we get a rational result because we've converted the string from input into a number, which is what we really want to use for multiplication. This is something that's very easy to forget, and if it happens to you, you will not be the first person who has ever done it, and you will not be the last person who will ever do it. Don't freak out about it. I've known some beginning programmers who look at this and say, whoa, functions inside of functions, that's a little bit weird. I'd like to do it in 2 steps. That's perfectly fine with me. I could say years as string. Oh, I'm sorry, I'm using the convention from a previous programming language. Years as string equals input of how old are you? And that will give me a string, and then I can say the years is the integer form of years as string. It's one extra step, but if it helps you to understand better what your program is doing, then by all means feel free to do it that way. You'll see that it has the same results. If I have someone named Henrietta who's 45 years old, it'll still work great. Let's give the discount program the same treatment, where we're going to ask for input so that it's not as inflexible. The description is going to be exactly the same, but in this case, instead of saying the amount is $19.95, we're going to ask for input. Let's do it in 2 steps for this first one. Instead of $19.95, we're going to input what is the price. In this case, I won't put the extra blank because having the cursor right up next to the dollar sign looks really good. And then the amount will be float of amount string. Remember, I need to have a floating point value with decimal points to represent money. I'll do the percentage as one step. It's the float of whatever input what is the discount percentage? And here again I have a nested function call. Let's run the program. When I test it, I like to use numbers where I know exactly what the answer is going to be in advance to make sure everything is working properly. If something costs $50 and a 10% discount, I should get $5. This gives me confidence that my program is working correctly. I can run it again, and now I can use any price I want with any discount I want. If something costs $45.99 and I have a 3.25% discount, I'm saving $1.49. Moral of the story: the input function puts up a prompt on the screen, waits for the user to type their answer and press enter, and whatever string they entered is returned to you. If you want a string, leave it as a string. If you need an integer or a float, remember to convert it. Otherwise, your arithmetic is going to not work the way you thought it would. In this video, we're going to talk about the print function. I'm going to write a program in the upper half of the Thani window, and whenever I write a program, I always start off with a short description of the program, my name, and the date that I wrote it, and then a longer description of what the program does and the purpose of the program, namely, given an age in years, calculate the approximate age in days. I'll want a variable to hold the number of years, and so I'll call that years. That's a fairly descriptive name. And I'll set that to my current age, which is 64. And then I'm going to calculate the total number of days, and that's going to be 365 times the number of years. And then I'm going to print days. This is the simplest form of the print function. You just give it a variable. Let's save that program. And I'm using Linux, by the way, so if you're using Windows or Mac OS, your save dialog will not look anything like this. And let's go to the .c020 file. And in there, we'll call this age1.py. And now let's run the program. And when I run it, I get the number 23,360. This works, but it's not ideal. If I gave this program to someone else and they ran it, all they would see is a number with no explanation. So whenever you print something, you really want to label it so that people who are using your program will know what it is you've tried to print. Print can print as many things as you want. So I can say your age in days is approximately, and then the word days. The variable days. That's an important point here, by the way. Days is not in quote marks, so that means I'm actually accessing the variable. I'm not printing the word days. I'm printing whatever is in the variable days. Big difference. This print function call is going to print the words your age in days is approximately, and then it'll print whatever's in the variable days. Let's save that and run it. And this time it says your age in days is approximately 23,360. So far so good. Remember I told you I could print anything I wanted, as many things as I wanted, so let's put a period at the end of the sentence. Save and run. Well, let me clear the shell first, because I don't want to interfere with the subtitles, the closed captioning at the bottom of the screen here. And let's run this again. And now it says your age in days is approximately 23,360, and there's a space before the period. That's because print always prints with spaces in between the items that you've separated by commas. Gee, wouldn't it be nice if there were a way to turn that off? Well, there is. One way to do it is at the very last thing to say sep equals and then an empty string. Sep stands for the separator. Now it's going to print the items that I've listed inside of the print without any separation between them. Let's save it and run. And this time it says your age in days is approximately 23,360, period. Because there are no separators, this means that if I want spaces in between words and numbers, I have to put them in myself. Put a space inside the first set of quote marks so that I will get the spacing between the word approximately and days. Save it and run it. And that's exactly the result I desired. Okay, there must be a better way, because this is a little bit clunky to have to remember when to put in spaces and when not to, and when to put in the sep equals and when not to. Turns out there is a better way. It's a little bit weird looking, but here we go. I'm going to say your age in days is approximately, and then an empty pair of curly braces. This is a placeholder, and then a period. That string, I'm going to say, I want you to format that and fill in the blank, those curly braces here, you can think of them as fill in the blank, with days. If I run that, I get exactly what I wanted. So there are two ways you can do it. You can say print a bunch of separate items and then use sep equals to make sure the spacing comes out right. Or you can make a single string and put in curly braces as placeholders and then pass that to the format function and tell the format function what things ought to fill in those curly braces. You can have as many sets of curly braces as you want, by the way. For example, I could say your name equals, in this case I'll put David, and then I could put here curly braces, comma, your age in days is approximately curly braces. Now I have two sets of fill in the blanks, which means that format has to have two things to fill them in. And so I'm going to format this string, filling in the first set of curly braces with your name and the second pair of curly braces with days. Save that and run it. Well, clear the shell first, excuse me. Got to remember those closed captions. And I'll say, David, your age in days is approximately 23,360. Format is really powerful. You can do a lot of wonderful things with it. Here's another program. In this program, I want to find out what a percentage is. In other words, what's 7.5% of something that costs, let's say, $19.95? My new program here is going to be calculate percentage of a monetary amount. And again, I'm going to put my name and the date. The purpose of this program is, given a price and a discount percentage, what is the amount of money to be saved? That's what I'm trying to calculate. Let's say my amount is going to be $19.95 and my percentage is going to be 7.5. So I'm going to have 7.5% of $19.95. Well, the amount that I saved is going to be the percentage divided by 100 times the amount. I can print that out as some percent of some monetary amount is another monetary amount. And I'll put a period at the end of my sentence, and I'll pass that on to the format function. There's three sets of curly braces. That means I have to fill in them with three variable names. So the percentage is the first one, The second set of curly braces is going to be my original amount, and the third will be the amount of money saved. When I pressed enter, you'll notice that it's indented for me. That's a signal that something is not right. Why didn't it go to the new line? The reason it didn't go to the new line is because I forgot to close my parentheses on line 9. I need that second set of parentheses, and now that gray highlighting goes away. I'm good to go. Let's save that, and let's call this discount.py. And clear the shell, run it. 7.5% of 1995 is 1.496249999. Oh my goodness, that will not do. We need to make format give us exactly 2 decimal places after the decimal point. The way you do that is inside the curly braces you put what's called a format string, a colon, and in this case I'm going to say I want decimal point 2 decimal places, and this is a floating number. I want that for the amount saved as well. And for the percentage, let's do the percentage of 3 decimal places, so I'm going to say :3f. Save and run. And now I get the percentages and the monetary amounts with exactly the number of decimal places that I desire. There's a web page I've written that describes some of the other things that you can do with these format strings. I strongly suggest you read it. And that's a whirlwind tour of the print function. Up to this point, we've been using Python as a glorified desk calculator. In arithmetic, you did calculations, then you moved up to algebra, where you used variables. In a similar way, we're now going to move from calculations in Python to using variables in Python. Similar but not identical, because variables in Python do not work exactly the same as variables do in algebra. Let's look at this statement in Python. You may be tempted to read it as x equal 42 because of that symbol in the middle. But what it really is saying is x refers to the value 42. As the book says, you should read that symbol in the middle as refers to, gets, or is assigned. The way Python evaluates this, and the way you should evaluate it, is to look at the value on the right-hand side first. Always, always, always start on the right-hand side. So that value, 42, goes into memory somewhere. And then the variable on the left-hand side, x, refers to the value 42. Let's follow that with another statement. X refers to 7.3. Again, we start on the right-hand side. The value of the right-hand side is 7.3, and that gets put into memory. Then we look at the left-hand side and say x now refers to 7.3. The 42 is left around in memory, and it'll eventually get cleaned up. What about using variables in further calculations? In this code, after the first statement is done, x refers to the value 7.3. In the second statement, y refers to x plus 1.2. We always, always, always start out with the right-hand side and figure out what it works out to. Well, what is x referring to right now? 7.3. That means we can substitute as 7.3 plus 1.2, and the right-hand side works out to 8.5, and that value goes into memory. Now and only now can we look at the left-hand side and find that the variable y refers to 8.5. So that's the status of memory at this point in our program. To drive home the point that the variables in Python don't work like the ones in algebra, let's look at this set of 2 statements.
At the end of the first statement, x refers to 5. That's what the first statement says. But let's look at that second statement. In algebra, that doesn't make any sense at all. 5 doesn't equal 6. But again, this isn't algebra. Instead, you're going to follow the rule. Whenever you see that symbol in the middle, you will always go to the right-hand side first and work it out completely. What's in x right this moment? X right now refers to 5, so that substitutes to 5 plus 1, so the right-hand side works out to 6. Now and only now can I look at the left-hand side and say, who's referring to that 6? Answer, x. So x now refers to 6 instead of the 5. What we've done, by the way, is called incrementing x. You'll see this pattern. X refers to x plus 1, almost said equals there. X refers to x plus 1, or x is assigned x plus 1. A lot in Python and a lot in programming, because it's very common to have computers do counting. The moral of the story: whenever you see something like that thing at the top, you read it variable refers to value, or variable is assigned value, or variable gets value. You go to the right-hand side first and figure out what that value works out to. Once you've completely worked it out, then the variable on the left will refer to that value.
In the book, you've read about floating point data values. What are they, and where does that name come from? In general, a floating point number is one that has a decimal, in contrast with integers, that is, whole numbers. As to the origin of the term, a bit of history. Back in the old days, when computers were primarily used in the business world, common business-oriented programming languages let you specify that a value had a fixed number of decimal places to the right of the decimal point. So a fixed decimal 2 value would always be represented with exactly 2 decimal places, no more, no fewer. The business world was happy with this. Scientists, not so much. To do scientific calculations accurately requires varying numbers of decimal places. In other words, the decimal point can't be fixed in place. It has to float according to the demands of the calculation, and that's where the term comes from. In many programming languages, the float data type specifically means a representation that takes up 32 bits, can represent numbers from 10 to the minus 38 to 10 to the 38th power, and is accurate from 6 to 9 digits. However, that's not a large enough range or precision for some scientific calculations, so there's another data type called double, which uses twice the space and gives you a phenomenally greater range and almost twice the precision. In fact, double is often called double precision for that very reason. In most Python implementations, the float class, which floating point values belong to, uses a double precision format internally to give you the best range and accuracy for your calculations. There are 3 types of errors that you can make in Python. The first type is called a syntax error. By the way, this number sign that I'm typing in the shell is a comment. That means Python should ignore it. It's just there for us humans to read. A syntax error happens when you say something that's grammatically incorrect in Python. So for example, if I try to say 34 plus times 8, that doesn't make any sense mathematically. It's just wrong on every possible level. So when I press the Enter key, the shell will respond, showing me that the star is where it got confused and says, that's invalid syntax. You can have another kind of error called a runtime error. This happens when you do something that is syntactically valid, it's grammatically valid. For example, if I try to evaluate 42 divided by 0. Well, syntactically, in terms of grammar, I have 2 numbers and a division sign between them. But when it comes time to actually run that calculation, I get an error that says zero division error because you can't divide by zero. These two types of errors are usually pretty easy to find. Syntax error is the easiest because the compiler points them right out to you, and runtime errors because once you run the program you see the error front and center. The third type of error is called the semantic error, which means you said something that's syntactically correct grammatically, and it's not going to cause any errors when you run the program, but it doesn't do what you wanted it to. So for example, if I wanted to find out how many days there are approximately in 25 years, and I accidentally typed 25 plus 365, there's nothing wrong with that in terms of mathematics. I have two numbers with the plus sign. There's no runtime error because I can certainly add 25 and 365, but the number I get is nowhere near the correct answer because I've said something that is a semantic error. I didn't do the computation I intended to do. Semantic errors in general are the hardest ones to find because the compiler can't help you, the runtime system can't help you. It's only when you as a human look at the error, at the result, and say, wow, this is not what I intended. Let's discuss the kinds of errors that you can get in Python. The first type of error you can get is a parse error, also called a syntax error. This happens when you say something that's grammatically incorrect in Python. For example, if I were to type 3 plus times 5, the shell would tell me that's invalid, and you'll notice that it points out where the error is. Let's open up a program that has an error in it. And you'll notice that there's a gray background on some of these lines. Thonny colorizes things, and when you see something in gray, that means that something is incomplete. But let's ignore that for the moment and try running the program and see what happens. And we have a syntax error, a parse error, in line number 3. Well, let's look at line number 3. It looks perfectly good. Parentheses are balanced. The division is proper. Why does it say line 3 when the error is really here on line 2 where we've forgotten the closing parenthesis? And the answer is, it's because of the way Python parses your programs. Have you ever buttoned your shirt and found out when you get to the bottom that you're out of buttons? Now, where did that error start? Did it start at the bottom, or was it somewhere up further on? The answer is usually it was up somewhere near the top and you forgot a button or a buttonhole, and that's why you're out of buttons when you get to the bottom. Python works in somewhat the same way. It's tootling along here at line number 2. This looks good. Equal sign is cool. Input, I know what that is. Here's my opening parenthesis. Here's a double quote. And here's the closing double quote. Oh, there's no closing parenthesis here. Maybe it's on the next line. And so it goes to the next line, finds the word AVG here and says, I can't go any further. Throws up its hands, gives up, and says, that's where the error is. I'm out of buttons. Moral of the story. When you get a syntax error, Python will give you the line number where it gave up, where it could not go any further and make a valid program. That means that your error may be on that line, and it may be somewhere above where the error truly started to happen, just like buttoning the shirt. Those are parse errors. The next kind of error we want to consider is a type error, which happens when you try to do an operation that was not intended for a data type. Let's take a look at this program where we fixed the closing parenthesis so we no longer have a parse error, and let's run it. Our first number will be 3, and the second number will be 4, and in line 3 it says, unsupported operand types for division, string and float. The reason this happened is because we got num1 and num2 as input, and remember, input always gives us back a string. The num1 plus num2 worked out okay because by coincidence we can add strings together. But when you have that string, num1 plus num2, and try to divide it by a floating point number, 2.0, Python says, timeout, you can't do that. You cannot divide strings and floats by one another. A third type of error that you can get when you're programming is called a name error. In this version of the program, we fixed the type error by putting in the call to float on lines 1 and 2. But we've introduced a new error on line 4 by using the word average when in line 3 the variable name was really avg. So let's see what happens when we run the program. The first number is 3, our second number is 4, and the program bombs out in line 4 because it says the name average is not defined. The fix would be to either change line 3 to be average or line 4 to be avg. And let me take my caps lock off while I do that. And now if I run the program, when I have 3 and 4, the average is 3.5. The fourth type of error that you'll encounter when you program in Python is the value error. And that happens when you give a function input that it wasn't designed to handle. I fixed the name error in this program by converting my inputs to floats in line 1 and 2. But if I give the float function bad input, for example by typing the word 3 instead of the number 3, I'll get a value error. It says, no, I can't convert THREE to a valid floating point number. Later on in the course, we're going to learn how to catch these errors and respond to them in a good way. Those are the four main kinds of errors that you'll encounter when programming in Python. The first few times that you get an error, you're sort of going to freak out and you're going to just have no idea what's going on. Don't panic, take a deep breath, look carefully at the error message, read it completely, figure out which kind of error it is, and then look carefully at the line where the error occurred, and again, because of our shirt buttoning problem, look a little bit above where the error was pointed out if it's a syntax error, and after a while you'll get used to seeing some of these errors come up. And when you see an error, you won't need to freak out. You'll say, oh yeah, I remember that one, and I remember how I fixed it, and your programming will go ever so much faster. In this video, we're going to examine something called a nested loop, a loop inside of a loop. Here's a program that we're already familiar with. It draws a pentagon. I have a loop variable, pent, that loops 5 times, 0, 1, 2, 3, and 4, goes forward 100 pixels, and turns right 72 degrees. And when I run it, I get a pentagon. What if instead of going forward 100, I were to draw a square instead? So that I would have 5 squares rotated 72 degrees apart each. Python lets me do that. I can say for square in range 4, go forward 100 and go left 90 degrees. So now I have a loop inside of a loop. My outer loop in line 12 has an inner loop in line 13. Lines 14 and 15 belong to the inner loop. Line 16 belongs to the outer loop. Let's run that and see what it looks like. And there's my pentagon of squares. Is it possible to nest a loop inside a loop inside a loop? You bet it is. I can put another loop here for try in range 3. And notice that it has indented this for me automatically, but now I'm going to have to indent all these other ones. So what I'll do is I'll highlight them all, and Thani makes this easy. Instead of having to do one line at a time, I just press tab and Thani indents everything for me. And then here, I have to go left 120 degrees. So I'm going to have a triangular pattern that is made up of a pentagonal pattern of squares. Let's run this and see what it does. How cool is that? Now it's your turn. Try drawing a hexagon of squares. Try drawing a square of hexagons. See what you can do by nesting loops inside of loops. Everything we've done up to this point has been in text. There's nothing wrong with text, but it would be nice to be able to draw graphics. We're going to use Python's turtle graphics to do our drawings. Imagine a robotic turtle with a pen in its belly that you can drive around on a piece of paper and it draws lines as it moves. Instead of needing a physical device, turtle graphics let us draw the lines on the screen. By the way, these turtle graphics are based on the Logo language developed at MIT by Wally Feuertzig, Seymour Papert, and Cynthia Solomon. I'm going to do most of my experimenting with turtle graphics in the shell. The first thing we have to do is import the turtle module or library. The next step is to create a window for the turtle to inhabit. So I'll have the variable window refer to the screen method inside the turtle library, and that will create a window for us. I'll move that to the side so we can see both of them at the same time. And the next step is to create a new turtle object. The book uses personal names like Alex and Tess to refer to the turtles. If you'd like to name your turtle after yourself or your best friend, feel free to do so. However, that's really not my style, so I'm just going to use the letter T to refer to a turtle object that's a capital T turtle on the function name from the small t turtle library. And as you can see on the right-hand side of the screen, there's the turtle, that little marker. It's facing to the east right now. You can now give commands to the turtle object to say, make it move forward 150 pixels. T.forward 150, and as it moves, it draws a line. You can also read this from right to left. It says, call the forward method that belongs to turtle T. You can make the turtle turn left or right. Let's go left 90 degrees. Unlike sine and cosine, which require radians, the turtle is more ordinary person friendly and uses degrees, so I can say T.left 90, and you'll see that the turtle is now facing upwards to the north. Let's go forward 100 pixels. And then right 45 degrees. And then forward another 50 pixels. And this time I'm going to abbreviate forward as FD to save myself a little bit of typing. You can use LT or left to turn left and right or RT as an abbreviation to turn right. To go backwards, you can use any of three different abbreviations. I can use the full word backward, or I can use back, or I can just use BK. And let's complete a simple design here by turning left 135 degrees and going forward another 50 pixels. There are plenty of other things you can tell the turtle to do. To erase everything the turtle has drawn so far and return it to its original position, use the reset method. T.reset. In order to preserve room for my subtitles, I'm going to clear the shell now as well. You can change the color of the pen using the color method. So let's use the word green, and the green has to be in quote marks. And you'll see that the turtle marker has turned green. The video description has a link to the list of all the color names that you can use. The color change is more apparent when we go forward. And you can change the background color of the entire window with the BG color method. So I can tell my window background color to be bisque, which is sort of a nice peach brownish color. I can make the pen width thicker by using pen size. So let's make the pen 3 pixels wide instead of 1. And you'll see the difference when I move forward. And I can change the shape of the turtle to look like a turtle by using the shape method and putting the string turtle as the argument. A complete, as in more than you ever wanted to know, list of the methods for the turtle and window are at the link that's shown in the video description. Here's a complete program that draws a square. It sets up the turtle on lines 1 through 9 by importing the turtle library, creating a window to draw into, creating a turtle, setting the window background color, and then the color, shape, and size of the turtle itself. And on line 9, here's a new function, speed. If you give it a 0, the turtle draws as quickly as possible. On lines 12 through 19, I draw a square by moving 150 pixels and turning left 90 degrees, and doing that 4 times in a row. And at the end, I hide the turtle, which leaves the square all by itself. Let's run the program and see what it looks like. And voila, there's the square. At this point, I suggest you just pause the video and go wild and draw anything you like from the shell. Then, try expanding the square program to draw a house by drawing a triangular roof up at the top. I've written that program, and here's what it looks like when it runs. This is without the fastest possible speed. So give it a try and start familiarizing yourself with turtle graphics in Python. There are 3 main structures in programming: sequence, repetition, and conditionals. Everything we've done so far is sequence, one command after another. Now let's look at the second structure, repetition. Consider this program that draws a square. Let's run it. And sure enough, that's what it does. This program goes forward 100, left 90 degrees 4 times. What if we had to draw a pentagon with 5 sides? That would require us to type forward and left 5 times. An octagon with 8 sides would require us to type or copy and paste forward and left 8 times, and it would be easy to lose count. What to do? But first, let's take a quick side trip and discuss calculating the angles for a regular polygon. For the square, we turned left 90 degrees because squares are all right angles. What if you want an equilateral triangle? You might think, oh, the angles in a triangle all add up to 180 degrees. So you'll write code like this. Let's go forward 100, and then left 60 degrees. And let's copy and paste it so we have a total of 3 times. Run the program, and it doesn't work. Why not? Pause the video and give it some thought before I reveal the answer. The problem is that the interior angles of a triangle all add up to 180 degrees, but that's not the perspective we want. The way we want to look at the problem is that we need to get the turtle back to its starting position in 3 turns for the 3 sides, and that's 1 full revolution of 360 degrees, so each turn has to be 120 degrees, 360 divided by 3. So let's change these 60s to 120s. And notice that's one other disadvantage of sequence. If I had 5 sides or 8 sides, I'd have 5 or 8 corrections to do. Let's run the program, and now the angle is calculated correctly. That's much more like it. That means if we want to draw a pentagon, 5-sided figure, we have to go 360 degrees in 5 turns, which is 72 degrees each, 360 divided by 72. Here's the beginning of the program for the pentagon. And instead of writing a forward and left and copying and pasting it to get 5 total, this time I'm going to write a for loop. I'm going to say the word for, and then a loop variable, the variable that controls the loop. And in this case, I'll call it counter, because I'm counting how many times I've drawn a side. The word in, and then a list of values that you want the counter or loop variable to take on. So 1, 2, 3, 4, 5, and then a colon. After the for is set up, you have the body of the loop, the things you want done that many repeated times. And in this case, I want to go forward 100 pixels and then left 72 degrees. After the loop is finished, I'm going to set the window background color to light blue. The body of the loop on lines 11 and 12 is indented under the for statement, and it must be indented properly. All the statements in the loop body must line up exactly at their left-hand edge, or Python will complain. Let me put in a mistake on purpose, and you'll see that Python complains that I have an unexpected indent. Indenting properly is easy with Thani because Thani helps you do it correctly. What's actually happening when we run this program? The loop variable counter refers to the first value in the list, 1, and then it does the body of the loop, which draws one side of the pentagon. The loop variable then moves on to refer to the next value in the list and does the body of the loop again. The loop variable counter proceeds to refer to the next value in the list, 3, does the body of the loop again to draw the third side of the pentagon. Counter moves on to the next value into the list, 4, does the loop body again, then counter loop variable moves on to refer to the next value in the list, 5, and does the loop body once more. That completes the pentagon. There aren't any more items in the list, so the for loop is finished, and the program proceeds to the next statement after the for. Again, it's important to note that setting the window background color to light blue is not indented, so it's not part of the loop body. It's outside the loop. Let's run the program to show that it does what we really expected it to do. And sure enough, it works great. This program doesn't use the loop variable in the body of the loop. Let's change the program so that each side of the pentagon is drawn in a different color. First, I'm going to change the list of values to a set of color names. Instead of 1, 2, 3, 4, 5, I'm going to set the strings green, red, blue, orange, and purple. There are still 5 items in the list, so the loop will be executed 5 times. I'll still get a pentagon. But in this case, the loop variable isn't really designed to count. The loop variable is telling us which color to draw the side in. So let's change its name from counter to something more appropriate, like side color. Then, inside the loop, before I draw the side, I'll set the color of the pen to be the side color. Let's run the program. And I get a multicolored pentagon. Let's do one more program that involves a for loop, but not a graphic one. I'm going to move the shell up a bit, and I'm going to clear it and create a new program. And this program is going to display the cube of the numbers 10 through 15. And as usual, I put my name and the date. First, I'm going to have a line that labels my output. I'm going to print the word number and cube. And now I'm going to set up my for loop. For counter in 10, 11, 12, 13, 14, and 15, the body of the loop will print the number and its cubed nicely lined up with my heading. I'm going to need formatted output for that, so I'm going to have my format string. This says print as an integer with 6 places, a space, and then another integer with 6 spaces. Format that and fill in the blanks with the counter and the counter to the 3rd power, the cube of the counter. And then I'll print the end when I'm out of the loop. So counter will first refer to 10, and it'll print 10 and 1,000. Then counter will refer to 11, and it'll print 11 and whatever 11 cubed is, then 12 and 12 cubed, 13 and 13 cubed, all the way up to 15 and 15 cubed. When I try to run this program, I have to save it with a name. Let's call it cubetable.py. And there I have my numbers and the cubes from 10 through 15 inclusive. There's an unanswered question here. What if we wanted the program to ask the user how many sides they want for their polygon? So they can say, oh, I want 8 sides, or I want 7 sides, or I want 12 sides. What if we wanted to ask them the starting and ending number of the cube table? Let's say they want the cubes of all the numbers from 23 through 37. In that case, we can't write a list of values for our for loop because we don't know in advance how many values we're going to need. We'll solve that problem in the next video. At the end of the last video, we were left with the question of how to use a for loop if we didn't know in advance how many times we would be repeating that loop. The answer to that question is the range function, which effectively produces a list of integers. Here's a program that uses the simplest form of range. For I in range 5, print I. In this case, my loop variable is just the single letter I rather than a word like counter. This is a convention among Python programmers. Common loop variables will be letters like I, J, K, or N. When we get to the discussion of lists, we'll see why this is a reasonable choice. Let's run the program and see what it produces. We see that it produces the numbers 0, 1, 2, 3, and 4. That means we did loop through 5 times. So range 5 is the same as if we had typed the list 0, 1, 2, 3, 4. When you have a simple range, the loop variable starts at 0 and goes up to, but not including, the number you specified. Why start with 0? Because if you're doing calculations with the loop variable, those calculations are almost always easier when you start at 0 than when you start at 1. Trust me on this. This simple form of range is exactly what we need to solve the problem of allowing the user to specify the number of sides they want for a polygon. Let me move the shell down a bit here and clear it out. Here's a program with the turtle initialization already done for us. I'll ask the user for the number of sides they want for the polygon. N sides is assigned the int of input of how many sides. And I'll also ask how long they want each side to be. Side length refers to the int of input of how many pixels per side. And then I need to calculate the angle that I'm going to turn when drawing the polygon. And that angle is assigned 360 divided by the number of sides. Now I'm ready for the loop. This time I'm going to use a more descriptive loop counter for side in range, n sides. I'm going to go forward the specified length, and this time I'm going to turn right by the angle that we've calculated. Let's run the program and see how it works. Let's say I want a 5-sided polygon at 100 pixels per side, and I get a large pentagon. Let's run it again and say I want 12 sides of length 37, and I get a 12-sided figure. Let's give it one more run and say I want a 6-sided figure with 120 pixels per side, and I get a giant hexagon. So the program's working just great. The next version of the range function comes in handy when you need to have a starting point other than 0. This will solve the problem of displaying the table of numbers in their cubes, where we let the user specify the beginning and ending number. Here's what this form of range looks like in the shell. For I in range 5, 9, print I. In this version of range, you specify the beginning and ending number. This example is the equivalent of writing the list 5, 6, 7, and 8. As with the simple range, the numbers that it produces go up to but not including the ending number. Here's the start of our program that does the table of cubes. Here's the start of the program that displays the numbers in their cubes. First, let's ask the user for the starting and ending numbers they want. Start refers to the int of input of starting number, and finish is assigned the int of input of ending number. Once I have the starting and ending number, I can print my heading, and then I can say for I in range start to finish plus 1. I have to add 1 because I want the finish number to be included, and remember, range goes up to but not including the number I specified. And now I do my formatted print. Two 6-space numbers, integers, and I fill in those formats with I and I cubed. Let's clear the shell and run the program. My starting number will be, let's say, 21, ending number 26, and there's the cubes of the numbers 21 through 26. Run it again. My starting number, let's say, is 45 through 56, And there are the cubes of the numbers 45 through 56. There's a third version of range that lets you specify the starting number, ending number, and step size between numbers. I'll show you that here in the shell. I can say for I in range 2 to 11 in steps of 3, print I. And this is prints 2, then 2 plus 3, which is 5, then steps 3 further, which is 8. 3 further would be 11, but remember I never include the final number, so this prints out 2, 5, and 8. I don't have a good example of a program that uses this version of range, but I do want you to know about it so that you can use it if you ever do need it. And that's range, the function that effectively produces lists of integers that you can use in a for loop when you don't know in advance how many times you need to loop. In this video, I'm going to draw a set of right-angle bookends. Each bookend will have a 50 pixel wide base and a height of 100 pixels, and they're going to be spaced 40 pixels apart. And here are the comments that say exactly that at the beginning of my program. Before I start programming, I'm going to draw a picture of what it's going to look like when it grows up. This doesn't have to be a fancy picture, as you can see here. I just want to get an idea of what it's going to look like, and most important, I want to add numbers to it so that I can see how much space I'm going to need everywhere. The red dot there in the middle, by the way, is where the turtle begins moving. My parents always used to tell me, "Do I have to draw you a diagram?" And my answer in this case is yes, you do have to draw me a diagram because it really helps me figure out what's going on. So, having this diagram in mind, I can now start the program. The first things we already know. I have to import turtle. I have to set up a window by calling the screen method, and I'm going to have a turtle T1, which is a turtle object. Let's draw the right bookend first. Looking at the diagram, the easiest thing to do will be to move 70 pixels east, and then I can back up 50, turn left, which will get me facing north, and go up 100 pixels. The question is, how do I move 70 pixels east without drawing anything? And the answer is to use the pen up method, which says bring the pen up off of the screen when you move. Then I can move forward 70 dots, put the pen down again, move back 70 dots, and that will, back 50 dots, and that will draw my 50 dot wide base. I can then go left 90 degrees and go forward 100. Rather than try and write the entire program before testing it, let's see if that part works. So I'm going to run that, and sure enough, I'm getting the bookend that I want. It's a bit thin, so I'm going to add something here. Let's add T1 dot pen size 3 to make a thicker line, and run again. And that's looking good. Now it's time to draw the left-hand bookend. I really don't want to try and move the turtle back to the beginning point or back to the far end of the left-hand bookend. So what I'm going to do instead is I'm going to create a second turtle. And it's going to start at the home position, right in the middle of the screen facing east. I can make it raise its pen, and this time I'm going to go back 70 pixels. Because I'm going to the left, I'm going west. Put the pen down. This time I'm going to go forward 50 dots. I'm still going to need to go left 90 degrees and then draw the vertical of the left-hand bookend. Let's save that and run it. And I forgot my pen size on the second turtle. So let's put that in, run it again, and now I have my bookends exactly as I wanted them. Did I really need to use 2 turtles here? No, not really. It turns out that there is a method for turtles called home. If you say home, that returns the turtle to its original place in the middle facing east without having to do a lot of work. So instead of creating that second turtle, I could have done t1.home and then gotten by just fine with 1 turtle. Let's show that. And oopsie, that doesn't work because I forgot to bring the pen up before I went home. This is the sort of thing that happens all the time. If you start writing without planning, you get weird results like that. Not a problem. We'll add a pen up before we return to the home position. And in fact, because the pen is up, I don't need this. I didn't delete the line. The reason I didn't delete the line is because just in case I'm wrong and I do need it again, I don't want to have to retype it. So instead I did what's called commenting it out. If everything works, I can delete the line later, but normally I will comment things out. So just in case I make another mistake, I can go back without having to do a lot of extra work. So let's think of what the computer is going to be doing. I've drawn my right-hand bookend. I take the pen up off of the screen, and then I return to the original place, and then I go back 70 pixels, which is exactly what I want to do because I still want the pen to be off of the screen. Doing the pen up again wouldn't hurt, but it wouldn't help either. This time it ought to work. And I've gotten by with 1 turtle. The question is, should you always use only 1 turtle, or should you use multiple turtles? Ask me if I care.
Do you care?
No, I don't really care a lot. I happen to be a 1 turtle kind of guy, and I like to do things with 1 turtle if at all possible. But there are some algorithms, some drawings that you want to do where it will be a lot easier and a lot more convenient to use multiple turtles. It's somewhat of a balancing act. If using multiple turtles makes things harder to read, then go back to fewer turtles. It's a judgment call. But I will not be disappointed if you do the assignments and get them done with 1 turtle or multiple turtles, as long as the program is done and working properly. The second thing we can take away from this video is that sometimes you will write a program and it won't come out the way you want. Don't panic, don't freak out. Analyze it, figure out what went wrong, and correct it. And that's the world of programming. Welcome to our world. We've already talked about modules and importing math earlier in the course. So what I want to start with in this video is the random module. In the shell, let's import random. And then if you use the random.random function, it will return you a random number between 0 and 1, excluding 1. So let's run it a few times here. And each time we get a brand new number from 0 up to but not including 1. For things like card games, you'd like to be able to generate random numbers in the range 0 to 51, which gives you 52 total. And for that, you have randrange. If you give it a single number, it generates a number from 0 up to but not including that number. So if I say random.randrange of 52, I get 39, and this time I'm just going to use up arrow to make my life a little bit easier. and each time I run it, I get some different number, and there's no guarantee that I won't get duplicates because, as you can see, I am getting those. If I were programming a dice game, I'd like to have a random number in the range of 1 to 6. So I can say random.randRange with a lower bound and an upper bound. This will generate a number from 1 up to, but not including, 7. So there's a 2, a 3, a 5, and so on. At this point, we can't write any dice or card games because we're missing the concept of selection, which we're going to see in Chapter 7. We can, however, use random numbers to generate random artwork. I'm going to go into a lot of detail about how I wrote and designed this program. And here's where the video may get a bit strange, as I'm going to be alternating between screen recording and a regular camera.
Here's what I want the program to do. I want to draw randomly sized triangles, squares, pentagons, and hexagons, all centered around the center of the screen. I'm going to take you through the steps I used to create this program, including a mistake or two, because it's important to see the design process in action.
Here's the general outline of the program. In lines 4 through 6, I'm going to import all of the modules that I need. In lines 8 and 9, I'm going to set up the turtle. And then starting in line 11, I'm going to draw 10 shapes where I randomly choose the length of each side and the number of sides that I want, and then draw the appropriate polygon. I can fill in part of this right away. The length of the side is going to be some random integer in the range 50 to 200 in steps of 10. My random number of sides is going to be a random number, again an integer, in the range 3 up to but not including 7, which will give me triangles, squares, pentagons, and hexagons.
The problem now is how to draw a centered polygon. I'm starting with the square first. I need to know how far to move from the center of the screen, and then I also need to know how far I'm going to have to turn the turtle, which is facing this direction, so that I'm oriented properly to draw the square. Let's label some of this. Let's call this distance that I have to move x, and this will also be x. Here's my polygon angle, which happens to be 90 degrees, or 360 divided by 4. This means these other two angles, let's call them theta, are 45 degrees, which is half of 90 degrees. Now, how can I find x? One way to do it is to drop a perpendicular to this side, whose length is side, and now I have another right-angled triangle. This right-angled triangle has a base of length side over 2, and its hypotenuse is x. Some trigonometry will tell me that the cosine of theta is equal to the adjacent side with that length over the length of the hypotenuse, and some algebra tells me that x is going to be side over 2 divided by the cosine of theta. How far do I have to turn to get oriented properly to draw the square? Right now, the turtle's pointing straight north. If I were to turn 180 degrees, I would be facing straight south. And then if I back off by theta degrees, that's the direction I want to point. So the angle that I have to turn by in order to start drawing is 180 minus theta.
Now that I have the math arranged, I'm going to temporarily set my program to draw only squares by putting a 4 in there, so I'll always draw a square. And then I'm going to put in the code for drawing the polygon. my polygon angle is going to be 360 divided by the number of sides. That's my interior angle, so to speak. And the theta is going to be my polygon angle divided by 2. The distance I have to move before drawing the polygon is going to be side over 2 divided by the cosine of theta. Theta is in degrees, but cosine wants radians, and that's why I have to do the conversion to radians here. For each shape, I want to return the turtle to its home position. I'll set the pen size to 3 to make it more visible. I'll go left 90 degrees and then forward by that distance that we calculated. And then to get the turtle oriented properly, right 180 minus theta. Drawing the polygon is something we've seen before. For count in the range in the sides, I'm going to go forward by the length of the side and then right by my polygon angle. Let's run this and see how it works. You'll see that I should lift the pen up when I move away from the center, but this is a good help at least to see that I'm doing the right thing. So that's looking good. Now let's put back the random range so I get a random number of sides and see how that works. Also, by the way, I'm going to set the turtle's speed to 0 so that it draws as fast as possible. And oh goodness, that's not what I wanted. I love the abstract look, but the triangles, the pentagons, and the hexagons are not centered as the squares were. So the question is, what's wrong here? This is what happened, by the way, when I was writing the program the first time. I got this result, and it took me about 15 minutes to figure out what's going wrong. It's this line right here, where I take theta as the polygon angle divided by 2. That's the correct angle for a square, but not for any other figure. Let's take a look at a pentagon. This interior angle here is 72 degrees. It's the polygon angle, 360 divided by 5. And my original formula was to say that theta is equal to the polygon angle divided by 2. So that would make this angle theta 36 degrees. That can't be right, because 72 plus 36 plus 36 doesn't add up to 180. It only adds up to 144. Since the sum has to be 180, the correct formula for theta is that it's 180 minus the polygon angle divided by 2. It was just an unlucky accident that this simplistic formula happens to work out to 45 degrees for the square, 90 divided by 2, and 180 minus 90 divided by 2 also works out to the correct answer of 45, and I mistakenly thought that this was the correct formula. It isn't. This is the one I have to work with. So instead of naively dividing by 2, what I really need to do is calculate the angle correctly, namely 180 minus my polygon angle divided by 2. And once I make that change, the code starts working very nicely. And then the only thing I need to add at the very end is to bring the pen up before I start drawing and to put the pen down when it's in position. And there's the program that I was looking for. The most important thing to take away from this is that I planned this program out. I drew a picture of what I wanted and I labeled it. That's not a guarantee that the program will be correct. I found that out when I had derived the wrong formula for theta. But that planning and the labeling and the drawing got me a lot closer to a solution than if I had just sat down and started hammering away at the keyboard. The book covers functions quite well, so there's not a lot I can add to it. You really need to read the material and, most important, use the code lens feature to step through the functions one step at a time. This will aid your understanding immensely. Here's a quick recap and some small amount of additional information. You can think of a function as a black box where you drop in some input value or values into the input hopper and receive some output value. The definition of the black box itself is done via the def keyword, DEF. The variable names a and b are called parameters. Think of them as placeholders. In terms of our diagram, they are labels for the input hoppers to our black box. And the return statement sends the value that follows it out the output hopper. When you call the function, you provide actual values, called arguments, that fill in the parameter placeholders. And the returned value becomes the result of the function call. A lot of people use the words parameter and argument interchangeably. Don't do that. Here's how you can remember which one is which. The arguments are actual values that fill in the placeholder parameters. Argument and actual both begin with A. Placeholder and parameter both begin with the letter P. The book uses code lens to go through the programs one step at a time. Thani has a similar feature used for debugging programs. To use this feature most effectively, go to the View menu and choose Variables, and a window will open up to show you your variables as you go through your program. Then choose Debug Current Script from the Run menu. This brings up a toolbar with three icons: Step Over, Step Into, and Step Out. To see absolutely everything that Python is doing, we're going to use Step Into in this video. Highlighted in yellow is what Python is currently looking at. It's starting with line 5, the definition of the function. It says, oh, I've got a function here, and when I step into it, it says, great, here's a function called average, and that weird number following the word at happens to be the memory address where the function resides, and we may safely ignore that. Python then moves to line 9, and it has to evaluate this statement. The first thing it has to evaluate is the right-hand side. It starts out by figuring what the arguments to average work out to. So as I step in, it shows that 3 works out to 3, and 6 is 6. Now it's ready to call the function. When the function call is made, Thani opens up a new window to show that function and its variables. So here's the function, and down here are what are called the local variables. And you'll notice that it's already filled in the parameters a and b with the arguments 3 and 6. Python needs to evaluate this assignment statement, so as we step in, we find that we use the right-hand side first, and now it needs to add a and b. It evaluates a, which is currently 3, and b, which is currently 6. So that works out to 9. 2 works out to 2, and now we can do the division. 9 divided by 2, which is 4.5, and that is what variable result will refer to, and as you can see, that has now been added to our variable list. Now we're at the return statement, and Thani has to, or rather Python has to evaluate result. Result is 4.5, and that's what gets returned to the caller. So the whole right-hand side of line 9 has worked out to the value 4.5, and that becomes the value that our new variable AVG refers to. The last statement in the program prints the average, and rather than go through that step by step, we'll do a step over which will do that statement all at once, which prints out 4.5, and the program finishes. That's how you use the debugger in Thani to go through a program one statement at a time to see exactly what Python is really doing. Whenever you have a Python function, all the names of the parameters and the variables that you define inside that function are called local variables. They belong to that function and nobody else can get to them. Consider these functions f and g. They both have a variable called z. The z that's used on lines 2 and 3 is local to function f. It belongs to f. The z that's used on lines 8 and 9 belongs to g. And this z here on line 13 is a variable that's been declared outside of any function. All three of these z's are totally independent of one another. It's as if each function is its own private universe, and this is exactly what we want, because it means we can use any variable names we want in our functions with an absolute guarantee that they won't conflict with the variables defined by anyone else in any other function. Parameters are also local. The x and y on line 5 are completely independent from the x and y that are used on lines 11 and 12. An important point to note is that the parameters get a copy of the arguments. The arguments themselves don't change. Let's step through this program in the debugger to see what's going on. We'll step over the definitions of f and g, and also the assignment of 2 to x and y to 3. They show up here in our variable window. And now let's go into the call to f. X is 2, y is 3, and when we make the call, we get a brand new window. A and B, our parameters, have been filled in with copies of x and y, the 2 and 3. And 2 times 3 is 6, plus 3 is 9, and that is assigned to the local variable z. When we return z, that window disappears. The parameters and the local variables are gone until we call f again. All we have is the return value of 9, which gets assigned to z. And so now we have z here from line 13, which has the value 9. Now let's look at the call to g on line 14. We'll step into it. X is 2 and y is 3. And when we make the call again, we get a new copy of the variables x and y. This x and y are totally independent of this x and y, and I'll show you why. If I step over this line, x plus equals 5, the local variable x becomes 7. The original argument x remains unchanged. Similarly, when I say y is y times 3, the local variable becomes 9, but our original argument stays unchanged. And when I execute this line, I get a local variable z, 63, which has nothing to do with our global variable z that's been defined in our main program. And again, when I return z, these local x, y, and z all disappear, and what's left is the return value, which gets assigned to w, our variable at the main area. And when I print z and w, I get 9 and 63. Many beginning programmers think you have to name the parameters the same as the argument variables, as we did in line 14 when we had x and y here and we named them x and y here. But there's no law about that. Remember, the parameters are placeholders and they can be filled in with any sort of arguments. Here in line 16, I'm using z and w and passing those in as the arguments for the placeholders x and y. On line 17, I'm not using any variables at all. I'm just passing raw numbers, 30 and 4, in to x and y. This means you can't guarantee that the parameter names will always match the variable names that you use in the call. The important point here is that the variables in a function are local. No function, or your main program either, can reach into another function to look at its local variables. In general, the way you send data to another function is through its parameters, and you send data back to the caller via return. However, a function can reach outside to look at a variable that has been defined previously. Consider this program that has two functions, both of which need to know the current tax rate. While I could have put the tax rate definition into both of my functions individually, that's a lot of duplication. And if the tax rate ever changes, I'd have to change it both in line 4 and in line 9, which could lead to unexpected errors. So instead, what I'm going to do is I'm going to define tax rate here in line 1 before I define any of my functions. Because it's been defined here outside, now all my functions can access it. You'll notice, by the way, that I've used all capital letters for the definition of this variable. This goes counter to what I usually do, which is all lowercase. By convention, when you see something in all uppercase, programmers know that's supposed to be treated as a constant. You're supposed to set the variable once and never modify it afterwards. Let's see how these global variables work. Let's debug this script. The tax rate is going to be set to 0.7. We'll skip over our definitions. And now let's go into the cell call. 5 works out to 5, 20 is 20. And now what we have is the price and the quantity, which are going to be copies of the 5 and 20 from our main program. And let's go and step into this. The price is a local variable, it's 5. Quantity is a local variable because it's a parameter, and it's 20, which works out to 100. And now we need 1 plus tax rate. Tax rate isn't defined here, but because it's global, because it's already been defined outside of our function, Python can look up and outside the function to get the 0.07, and all is well with the world. We return the result as 107, and the rest of the program would continue as normal. The same thing would happen if we went into buy. 5, 20, and 0.05 become the parameters discount, price, and quantity. And now as I evaluate this whole expression, I'm going to eventually need the tax rate, and again it will get my global value here of 0.07 and do all of the calculations and return that result. Remember I said that programmers see the all capital variable names and that's a constant and they know they're not supposed to modify it? Well, what if I did want to modify tax rate inside one of my functions? The answer is it can be done, but don't do that. And I'm not going to show you how to do it because it's bad programming practice. It's not a good idea to allow all your functions to trample all over global variables, because if cell were to change the tax rate globally, then when I went to go and buy, I'd have a different tax rate than the one I expected, and things would get really bad. So here's the summary of the whole video. Parameters and the variables that you define inside a function are local. They exist only as long as the function is doing its job. The moment the function concludes and returns, the parameters and the local variables disappear until the function is called again. You can define variables outside all your functions, and those will be globally accessible for reading only to your functions. Use global variables like this only for constants that many functions will need. In Python, you can put if statements inside of if statements, and that's called a nested if. Here's a program that asks for a price and quantity and calculates the subtotal, the tax, and the total and prints them out. Let's run it. If I have a unit price of $4.50 and I order 7 of them, there's my subtotal, tax, and total. I'd like to be sure that both the price and quantity are greater than 0. Let's add an if-else for the price. I'll ask for the price, and then if the price is greater than 0, I want to do everything else. I could indent them all by hand one by one, but Thani gives me a helping hand. If I highlight all the lines and press Tab, it indents them all. Let me hide the shell here so that you can see the whole program. If the price is greater than 0, continue with everything else. Otherwise, print price must be greater than 0. Let's go back to the shell and run the program. This time, if I enter a unit price of negative $4.95, it'll immediately tell me that the price must be greater than 0. Cool, that handles negative prices. But what about negative quantities? If I give a valid unit price and a negative quantity, it still goes through with a bad calculation, so I need another if-else to handle that. After I get the quantity, I have to ask if the quantity is greater than 0. If that's the case, I'm able to do all this stuff. Otherwise, the quantity is 0 or negative, and I print the quantity must be greater than 0. I have an if from lines 9 through 18 inside an if from lines 7 through 19. Let's run the program with a valid unit price and quantity. Everything works nicely. With an invalid price, it gives me an error right away. And with a valid price and a negative quantity, it gives me an error message as well. The program is now working the way I want to because I have a nested condition, an if within an if. Can you have an if statement inside the else portion? Yes, indeed. Here's another way I could have written the price program. In this program, I'm asking for both the price and quantity before I do any testing. Then I ask, is the price greater than 0 and the quantity is greater than 0? If both of them are okay, it's okay to do the calculations. Otherwise, one or both of the price or quantity must be wrong. In the else portion, I'm going to have a nested if statement, a unary if. If the price is less than or equal to 0, then it's bad. I need to make a print statement for that. Separately, I have to ask if the quantity is less than 0. If it is, I give an error message. There's no else needed for either this if in line 18 or this if in line 21, because the only way I can get here is if the price is less than or equal to 0 or the quantity is less than or equal to 0. If they were both greater than 0, I would have handled it here. Let's view the shell, clear it, and run the program. If the unit price is $4.50 and I order 10 of them, everything works great. If the unit price is negative, and I order 10 of them, it tells me the price must be greater than 0. If the unit price is okay, but the quantity is bad, it tells me the quantity must be greater than 0. And if both the unit price and the quantity are bad, it gives me both error messages. There's an important point here. In order to do a good test of my program, I have to test all the combinations of good and bad input to make sure I've covered all the cases. Another thing to notice is the difference between this program and the other one. In the first version of the program, as soon as I got an error, I gave the error message. In this program, I wait until I have all the input before I give any of the error messages. Which approach is better? That's a design decision. The takeaway from this video is that it's possible to have if inside of if, and if inside of else, and if the condition warrants it, you could even have an if inside of the if as well as an if inside of the else. Whatever the design of the program requires, you may nest ifs and elses inside of one another to get the effect you need. Up until now, we haven't been able to test for conditions. When we ask a person for their age in years, as in this program, if they enter a negative number, we do the calculation anyway, even though it doesn't make any sense. We'd like a way to tell if the input is valid before we do the calculation. And that's why Python has the binary if statement, which has this generic model. If some Boolean expression evaluates to true, we do some statements. Otherwise, the expression worked out to false, and we do other statements. That's a bit abstract. So let's put a binary if into this program. We're going to say if the years is greater than 0, everything's okay, and we'll indent the things that we want to do as the result of the if. We want to calculate the days, and we want to print the result. Otherwise, the years is not greater than 0, so we need to print age must be greater than 0. Let's run the program again. This time, if I say the age in years is 35, it does the calculation. Run it again, give it a negative 24, and it gives me the error message that age must be greater than 0. In most cases, you're going to have an else to go with an if. You'll want to do one thing or some other thing. Sometimes, though, you'll want to have an if part only without an else to go with it, and that's called a unary selection, one way, as opposed to this binary selection, which is two-way. Let's add some code to ask for the user's name and print it in the output. Name equals input of what is your name, and here in the output we'll put another placeholder and add name to the things to be output. Let's clear the shell and run it. So if your name is Nancy and you're 42 years old, that's Nancy's age. What happens if I press only enter for the name and then put the age in years? It says you're about 15,330 days old, comma, period. And that's fairly ugly. Let's put in a unary selection to provide a name if the user hasn't given us one. If the name is equal to the empty string, and notice I'm using two equal signs here. Remember, a single equal sign means assignment. A double equal sign is asking a question. Are name and the empty string the same thing? That's a yes or no, true or false question. If the answer is true, then we're going to set the name to mystery user. We don't need an else. If the name wasn't the empty string, it's the name they entered and it's the one we want to use. Let's clear the shell and run it. First with a name like Fred, who's 19. And let's run it again, this time with no name, 19. And it gives us the name mystery user instead of Fred. And the output is a little bit more humorous and at least not as ugly as it was before. Some people like to have an else with their if no matter what. If you're one of those people and you insist on having an else, Python has a construct for you. I can say otherwise, else, pass. Pass is a special keyword that means do nothing. Lines 6 through 9 now tell us if the name is the empty string, I set the name to mystery user. Otherwise, I have a valid name, pass on to the next statement, nothing is needed here. And this also works. If I give a name and an age, it works fine. If I don't give a name and give an age, it works exactly as before. To summarize, there are two types of if statements. One is the if with else, where you have two choices. You do one thing or the other. If the years is greater than 0, it's valid. If the years is not greater than 0, it's not valid. That's a binary selection. The other kind is a unary selection. If the name is the empty string, we'll set the name. Otherwise, there's nothing to be done, and so we don't even need the else part. However, if you're one of the people who insists on having an else for every if, you can always use pass to tell Python, do nothing. Here's a program that prints a stage of life given an age. It's written as a series of independent unary if statements to test age ranges. Let's say I enter an age of 7. 7 is not less than 0, so I don't print that. 7 is not greater than or equal to 0 and less than 2, so I don't print infant. 7 is not greater than or equal to 2 and less than 4, so I print the skip on line I skip the print on line 11. 7 is not greater than or equal to 4 and less than 6, so I skip the print on line 14. 7 is greater than or equal to 6 and less than 13, so I'm going to print out grade school. I continue on to the next if statement. 7 is not greater than 13 and less than 18, so I won't print teenager. And 7 is not greater than or equal to 18, so I won't print legal adult. The only thing that I will print out is grade school, and that's the correct thing. Let's run the script and view the shell and put in a 7, and sure enough it prints out grade school. There's nothing wrong with this program. It works exactly as advertised. But it could be improved. Notice that once we find out that the age is between 6 and 13, we don't need to do any of the other tests. This is a place where we'd like to use else's to save ourselves some computation. So let's rewrite it this way. If age is less than 0, that's not a valid age. Otherwise, let's test to see if it's greater than or equal to 0 and less than 2. If that's the case, we'll print infant. If that's not the case, then we nest yet another if statement and ask, well, is it greater than or equal to 2 and less than 4? And so on. I can nest my ifs inside of the else clauses, and that will guarantee that only one of the ifs will be matched. There's some extra optimization that I can do here as well. If the age is not less than 0, let's say they entered 7, then I know for sure that it's not greater than or equal to 0, so I don't need this test at all. Similarly, if the age is 7, it's not less than 2, so I know it's greater than or equal to 2. in the else clause, there's no need for me to test that again. I could go through by hand and indent all of these, but to save a little bit of time, let me show you what this looks like when we're done. And here it is. Now if I enter a 7 for the age, it's not less than 0, 7 is not less than 2, it's not less than 4, it's not less than 6, but it is less than 13, which means we print grade school, and we skip this else. It's not needed. So our program is now a little bit more efficient. Let's run it and see that it works. Let's clear the shell, view it, and run. And if the person is 7, they're in grade school. Again, the program works. There's nothing wrong with it. It's a little bit better than the previous version. The only problem we have now is that we're indenting and we're marching off the right-hand edge of the screen, and it's hard to read, and it could get confusing if we had more choices. There's a shortcut that you can use in Python. When an else is immediately followed by an if, you can combine them into the single keyword elif. And then I can unindent this. Here's another else that is followed immediately by an if, so I can combine those into elif and make sure my indentation is correct. The same with this else if can be combined into the keyword elif, and so on and so forth. Again, to save time, I'm not going to do all of them. I'm going to show you what it looks like when it grows up. This is a lot more readable, and it does the minimum amount of testing. Again, let's go with age 7. Is 7 less than 0? No. Well, otherwise, if 7 is less than 2, which it isn't, otherwise, if age is less than 4, otherwise, else, if age is less than 6, 7 is not less than 6, otherwise, if age is less than 13, which it is, we print grade school, and then we can skip all the other elifs and elses. Let's view the shell, clear it, and run this version of the program, and again, a 7-year-old person is in grade school. The moral of the story: if you have a program with a chain of conditions, if some condition is true, otherwise if some other condition, otherwise if some other condition, otherwise if yet another condition, otherwise last case, you can take all the else ifs, and instead of having to indent them, you can combine them into elif, and then all your cases will line up nicely, your code will be more readable, and you can get away with a lot less computation to get the results you want. A for loop is great when you know in advance the number of times you want to go through the loop. In the cases where you don't know in advance, you need the while loop. Let's look at the while loop using something called the hailstone sequence. Here's how it works. Start with a number, in this case 17. If the number is odd, you multiply by 3 and add 1, giving you 52. If the number is even, you divide by 2. 52 divided by 2 gives 26. 26 is even, divide by 2, giving 13, which is odd, meaning you multiply by 3 and add 1. As you see, the numbers move up and down, much as a hailstone moves up and down in the clouds before finally coming to Earth. In this case, coming to Earth means ending up at the number 1. And it takes 12 steps to get there. The question is, how many steps does it take for a number to converge to 1? And there's seemingly no pattern to that. Some numbers have a short sequence, others have a very long one. For example, if you start with 52, it takes 11 steps to get to 1. If you start at 51, it takes 24 steps. Here's the logic for a program that implements the hailstone sequence. We'll get a number and set our count of number of steps to 0. If the number is not equal to 1, then we're not done yet, and we have to ask if the number is even, in which case we divide by 2, or not even, in which case we multiply by 3 and add 1. That's one more step added to the count, and then we come back to ask, is our new number not equal to 1? If it's not equal to 1, we have to go through the whole process again. Eventually we'll get down to a 1, so number not equal to 1 will come back as false, and we'll print the count, the number of steps that we took. This bold red line here is our while loop. It comes back after we add the count. We come back and test again. Now let's look at the Python code to implement this. At the top of the program, I've taken that flowchart and expanded it into text. On line 10, I ask for the number. And on line 11, I set the count to 0. Line 12 is where the magic happens. As long as the number is not equal to 1, I have to do the body of the loop, which is on lines 13 through 17. I know that's the body of the loop because it's indented one level from the while. For odd numbers, I multiply by 3 and add 1. Otherwise, I divide by 2 and add 1 to the number of steps. When I finally reach 1, 1 not equal to 1 is false. I drop out to line 19 and print the number of steps with the count that I've accumulated. Let's view the shell and run the program, this time with 17, which takes 12 steps. If I start with 51, it takes 24 steps. If you want to see the process in action, you can print the number here. And then you will see inside the loop every calculation that has been done. If I type 17, you'll see the sequence 52, 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, 1, which took 12 steps. One other thing that I have to point out here. What happens if I run the program and start with 1? The while loop exits immediately and I have the number of steps as 0. This is an important concept in a while loop. If the condition comes false immediately, the body of the loop will never be done. I entered a 1 for the number. My count was 0. 1 not equal to 1 came out false immediately, so I dropped down to line 20 and printed the number of steps as 0. Let's look at another use of while, getting input until the user tells us they're finished. Here's a program that asks users to enter prices of items and gives them a total when they've finished. But again, here we don't know how many items they have. They may have 1 item, 10 items, or 50 items. We're going to set up a sentinel value, a special input value that indicates that there are no more data items coming in. In this case, we'll use -1 as the price because nothing can cost -$1. That will be our sentinel value. We start off by setting the running total to 0, and we set up a Boolean variable called more input, initially true, meaning I'm waiting for more input. I'm going to run the program so I can do the narrative along with the code. I'm waiting for more input. More input is true. That's why I'm asking for the price, or -1, to finish. I'm going to enter $8. $8 is not equal to -1, so it'll add $8 to our running total. We return to line 6. More input is still true. We're still waiting for more input, and that's why I got the prompt again from line 7. This time I'll add $4.50. $4.50 is not equal to -1, so that will get added to the running total. I come back up here. More input is still true, and I again prompt for a price. This time I'm going to enter my -1. Since -1 is equal to -1, I'll take the else branch of this selection and set more input to false. Once that happens, I come back to line 6 and ask, is there more input? This time I get false, and I'll drop down to line 12 and print the total of $12.50. Finally, you can use while loops to repeatedly request input until you get a valid value. For example, your program might ask users a yes or no question. You want to make sure they either type the letter Y or the letter N. If they type the letter X or something else, you want to prompt them again and say, no, really, give me a Y or N. That's what this function, get yes or no, does. You give it a message, the prompt to be displayed. It starts by setting the valid input to false. Before you ask for input, you don't have valid input yet. As long as you don't have valid input, the program will put up the message and get your input and convert it to uppercase. If you gave me a Y or an N, then that's valid input, and I'll set valid input to true. Otherwise, I'll tell you to enter Y for yes or N for no. The loop will come back, and if you did give me a Y or N, valid input's now going to be true, not true is false, and I'll drop out and return the answer. If you didn't give me valid input, I'll go through lines 5 through 10 again. This is the we're going to keep doing this until you get it right loop. Here's the main program. I'll call get yes or no with the prompt, do you like carrots? Y/N. I put this Y/N here so that the user has an idea of what to expect to put in for valid input. Get yes or no will return either the letter Y or the letter N into the variable carrots. If carrots equals Y, I'll print one response, otherwise I'll print a different response. Let's run that script and view the shell. If I type an X, please enter Y for yes or N for no. This is the loop in action. It's going to keep asking me again and again and again until I finally type a Y or an N. This time I'll go with Y. And the program ends telling me I like them too. Let's run it again. Check with invalid input and then valid input. And the program works. The key point of this video is that the while loop lets you repeat some actions as long as some condition is true. You don't need to know the exact number of iterations in advance. This video isn't very highly scripted, and I'm going to be doing most of it in the shell, so you have been warned. We've been using strings a lot in this course. A string is 0 or more characters inside of quote marks. You can use single quotes like this, or double quotes like this, or triple quotes if you need a multi-line string. And you'll notice the \n, which is Python's way of saying, give me a new line. A string can have one single character in it, and there's a special string called the empty string that has no characters inside of it at all. Even though it doesn't have any characters between the beginning and ending quote marks, it is still a perfectly valid string. We've seen that you can add strings. For example, door plus bell adds them together. The official name is concatenates them, and we get a single string, doorbell. You can also take a string and multiply it by an integer, and it repeats that word as many times as you need. There are no other arithmetic operators that work properly with strings. Strings are objects. With numbers, we would usually give the number as a parameter to a function. For example, the absolute value of -3.7. With strings, however, we need to use the dot notation as we did with turtles. Let's create a couple of variables here. Let's make the word playground, and let's make a sentence. This is a sentence. And let's have a variable called shout, which is all in uppercase. If I want to convert the word to all uppercase, I can't say upper of word. I can't use it like a number. Instead, I have to use the dot notation and say word.upper. This sends the upper message to the word if you're reading from right to left. And the result is playground in all capitals. In a similar way, I can say shout.lower, which will convert all the letters in the string to lowercase. The exclamation point isn't a letter, so it remains unaffected. There's also the capitalize function. If I say sentence.capitalize, it converts the very first letter in the string to a capital letter. Notice that it capitalizes only the first letter. It does not affect any of the rest of the word, so it won't capitalize every word. It would be nice if you could do that, and later on in the course I may show you a way to make that happen. There is one exception to this dot notation. If I want to find the number of letters, or number of characters, that are in a string, I can't say word.length. That doesn't work. I have to say length of word. So that's the one exception to dot notation. I've shown you upper, lower, and capitalize. Another useful function is strip, which gets rid of leading and trailing white space on a string. White space is defined as blanks or tabs or new lines. Let's take a look at this program. It asks, what's your name? And tells you that's a nice name. This sep equals empty string at the end tells Python not to put extra blanks between the items that it prints. Let's run this and run it legit. I'll say my name is David. It says, that's a nice name, David. You'll notice that the cursor for the input was right next to the question mark. What happens if somebody decides that they're going to do this? What's your name? They'll put an extra blank and they'll say Joe. And let's put a couple more blanks at the end. The problem is that your name has those blanks inside of it, and so they'll say, that's a nice name, comma, blank, blank, Joe, blank, blank, exclamation point. Hardly a nice thing to look at. Here's what we're going to do. We're going to say that the new name is equal to yourname.strip. And then instead of printing your name, we're going to print new name. Now when we run it, if they say their name is Joe, the extra blanks at the beginning and end are gone. We can use capitalize. We could say this. We could say new name equals new name.capitalize, which will now replace the old version with the capitalized version. And if they say Joe, everything looks really nice. Instead of doing it in 2 steps, I can make a chain of function calls. I can say, take your name, get rid of the leading and trailing blanks, and then capitalize that. So I can do it all in one line as a chain of function calls. Now if the person says their name is Nancy, everything works out exactly as it is, and it's a very convenient way to do a series of function calls all in one go. There are a couple of other functions that you might find useful. If I say word.elstrip, it gets rid of blanks or white space at the left. If I say word.rstrip, it gets rid of trailing white space at the end of the word. You can also use strip in another way. I don't see this a lot, but it's there if you need it. Let's say I say that the word is equal to dash 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 something and 3 dash 4. Well, let's make a bunch of dashes there. I can now say word.strip and tell it what the character is that I would like to get rid of. So I want to get rid of dashes at the beginning of and end, and it does that. Again, I haven't seen a lot of use for that, but if you ever need it, there it is. One other useful thing to do with strings is to find out if one string is contained within another. Let's go back to the word playground. And I want to find if the letter A is anywhere in playground. I can say word.find and give it the letter A, and it'll say, yes, it's at position 2. What does position 2 mean? Well, it turns out that you can treat a string as though it were a list of characters. So when I have the word playground, the P is at location 0, the L is at location 1, the A is at location 2, and so on. In fact, I can extract any character I want to by saying this. If I want the word character at position 3, that gives me the letter Y, word sub-0, and later on, by the way, you'll see why I'm calling it word sub-0, why I read it that way, is the letter P. This is called indexing. The indexing operator is a square bracket, and the number in between the square brackets is the index that you're looking for. What would happen if I tried word of -1? The answer is it would give me the last letter in the string. Word -2 would give me the N. What happens if I go off the edge of the universe? The length of the word is 10. So if I try to get to word 11, it'll say the string index is out of range. That index number is too big for the word. Same thing if I go off at the negative end. If I say word sub -11, it'll say that the word index is out of range. Let's go back and look at word again. I can do find for more than one character. If I want to say word.find YGR, does YGR exist anywhere in playground? The answer is yes, starting at position number 3. What if I try to find something that isn't in the word? Like Igor. Answer is it gives me back a -1. That doesn't mean it's the last character. The -1 is special. It means not found. Let's take another word here, like bookkeeper. I like that because it has 3 sets of doubled letters in a row. And I want to find the letter O. It will find the first occurrence. It won't find all of them. It will find the first O, which is at position number 1. Similarly, other dot find of K will find it at location 3. 0, 1, 2, 3. So find gives you the index of the first occurrence of a string inside of another one, or -1 if it's not there at all. There's a function called index which does something similar. If I say word.index of GRO, it'll give me 4, and that's correct, because if we look at it, 0, 1, 2, 3, 4 is where GRO starts. However, if I try and find something that's not in the word, like GROW, it'll give me an error. If you want your program to give an error when something isn't found, use index. Most of the time, though, you'll want to get back a -1 rather than getting an error, so that your program can continue and do something useful, usually using an if statement. In the previous video, we saw how to get a single character from a string by indexing with the square brackets. You can get a section of a string by specifying a slice. Let's make a variable called string and set it to recasting. If I write string square brackets 2:6, that means to take the slice starting at index number 2, the C, up to but not including the last number 6. And that gives us CAST. If you leave out the last number on a slice and just put the colon in a square bracket, the slice goes all the way to the end of the string. If you leave out the first number, the slice is presumed to start at the beginning, index number 0. And if you leave out both numbers and just put in a colon, you get the entire string. Let's talk about comparing strings. Strings are compared in what's called lexicographical order. So the string A is less than the string B, as one would expect, and ant is less than bison, and AUNT is greater than ANT. Here's something that may surprise you. If I ask, is ant less than capital Z zebra, I get false. Why is this? Because the way strings are represented, the lowercase a has a numeric value that is greater than the numeric value for an uppercase Z. You can see what the numeric codes are for a character by using the ORD function. The ORD of lowercase a is 97, whereas the ORD of capital Z is only 90. And that's why ant sorts after zebra with a capital Z. Strings are immutable. You can't change a letter within a string. Let's create a variable verb that has the word play. If I want to try to set the first letter to the letter C to end up with clay, I can't do that. The string object does not support item assignment. If I want to change a string, I have to create a completely new string. I can say this: noun equals the letter C plus the slice of the verb from position 1 onwards, which is the L, A, and Y. And then noun contains what I want. A lot of string manipulation involves going through the string one character at a time, and you can use a for loop to do that. If I set the verb again to play, I can say for character in verb, print that character, and it gives each character in turn. Sometimes you need to know the character and its index value. No problem, use a counting loop. For index in range, len of verb. Well, the length of our verb is 4, and so range will give us 0, 1, 2, and 3, which are the index values of the beginning, next, and so on characters. I can then print index and the character at that location inside the verb, and I'll get the index and the value both if I need those for my program. An extremely useful operator for strings is the in operator that tells you whether one string is contained in another. For example, is the word cast in recasting? Yes, it is. Is the word read inside the word predicate? Answer is true. If I ask if the word red is in bread, the answer will be false. The opposite of the in operator is the not in operator. So if I ask, is red not in bread, that will come back as true. Let's use this to write a program that takes all the vowels out of a string. We'll start with a comment that describes what the program does, and let's write a function to do that called remove vowels, and it'll take a single parameter s, which stands for our string. This is very common in Python programs. They'll use either s or str to represent a generic string. Since strings are immutable, we can't change s, so we're going to have to create a new results string which starts off as the empty string. For each character in our string s, we're going to ask, is the character not in the string of vowels? If it's not a vowel, we want to keep it, so we'll add it to the end of our result variable. Otherwise, it is a vowel and we'll pass. We won't do anything to our result. Once we're done, we can return that result. Let's save that and run it to make the definition and test it really quickly in the shell. If I say remove vowels, this is well, let's have all the vowels in there. So beautiful orders. That should contain all of our vowels, and it got rid of all the vowels for us. Now that I know my function works, I can write my main program. In my main program, I'm going to ask the user for a sentence, which would enter a sentence, and then I'll convert it to something with no vowels by calling remove vowels, and sentence is the argument that goes to the function, and then I'll print no vowels, and don't forget, invoke main, otherwise the program won't do anything. Let's clear the shell, and let's run the program. And for a sentence, let's say, taking out vowels makes things hard to read. And that's what we get as a result. In order to do the assignment, you'll need one more function that isn't covered in the book. And it's not in the book because it involves lists, which are in the next chapter. But you're all pretty sharp people, so I know you can handle this. Just consider it as a preview of coming attractions. The function we're going to investigate is called split. Let's say we have this variable, phone equals 408-555-1212. If I wanted to get the area code, prefix, and number as three separate strings, I could do something like this, phone.find of dash, to find where the first dash was, and then use slices to separate the string into its component parts. But it's much easier for me to say this, parts equals phone.split, and tell it the character or characters that I want to use for splitting. If I now print parts, you'll see I have a list in square brackets of three strings, 408, 555, and 1212. I can then assign those to individual variables. I can say area code equals parts 0, prefix equals parts 1, and number equals parts sub 2, and then print area code, prefix, and number individually. If you don't give an argument to split, it divides the string on white space, blanks, tabs, and new lines. If I set my sentence to be 4score and 7 years, and then say word list equals sentence.split with no argument in the parentheses, if I look at the word list, it split it up into the words exactly as I wanted. I can now use a for loop to go through the list as well, just as you saw in Chapter 4 when we introduced the for loop. I can say for word in word list, print word, and that'll print each word on a line all by itself. Knowing this, we can write a program that goes through a sentence and builds a new sentence with each word reversed. So the string, for example, would come out as Rolf Maxi. That's the program we want to write. A bit useless, but it gets the point across. Let's put the comments in here to tell what the program does. Accepts a sentence and then prints it with each word in the sentence reversed. First, we're going to need a function to reverse a string. Let's define reverse with s as the parameter. We're going to need a new string as the result, which starts as the empty string. And then for each character in the string s, we're going to say the new value of result is equal to the character we have plus the old value of result. This adds the characters at the beginning of the string, not at the end. And we return result. Let's save that, run it, and then we can test it here in the shell. If I say reverse example, works like a champ. Now the main program, which prompts for input, splits it into words and calls reverse for each word, and creates a brand new string with the backwards or semi-backwards sentence. We're going to define main to say that sentence is input of enter a sentence. We'll get our word list by splitting the sentence on white space. And we're going to need a string for our result. Let's call it backwards, and again it starts off as the empty string. For each word in the word list, we're going to set backwards equal to its previous value plus whatever we get from reversing the individual word plus a blank. This extra blank is to separate the words when we build our output. When we're done with all the words, we'll say backwards equals backwards dot strip to get rid of that last blank at the end, and then print the result. Let's save, clear the shell, and run. And it's not doing anything because guess what? I forgot to invoke main. This is a common error, so don't feel bad if you did it. I do it too. Let's run that again, and the sentence will be useless but instructive program. And there it is with each word reversed. So that's how you can use split to split a string into a list of substrings and then process them one at a time. Throughout the videos, you may have noticed me reading code like this as x equals 3725, y equals x sub 0. What's that sub all about? Let's take a look back at algebra, where you might have seen something like this. It looks a lot like our lists, except that the index number is written as a subscript. When computers first started being used for scientific purposes, programmers needed to represent lists like this, but they couldn't do subscripts on a teletype or punched cards. And they couldn't write something like this and read it as x1, x2, x3, because those are the names of independent variables, not part of a list. Those early programmers came up with a solution. They put the index number in square brackets to represent the subscript. In fact, in a language called Fortran, one name for lists was subscripted arrays. And that's why we use brackets for indexes and why we read them as x sub 1, x sub 2, etc. That's the story of sub. Let's consider this program to get the average of 7 days worth of temperatures in degrees Celsius. Let's run it, and it tells us the average temperature is 28.3 degrees. Nothing remarkable here, except it's very repetitive. We need an individual variable for every one of the temperature measurements. What if we had a whole month's worth of temperatures? That would be really difficult. We'd have a lot of copying and pasting with a lot of room for error. And can you imagine what line 12 would look like if we had to add 30 numbers up all together? Instead of having a separate variable for each day, we can use a list to group all of the values together under one name. If you think of an ordinary variable as a mailbox for an individual house, you can think of a list as a row of mailboxes for an apartment building. They all have a common street address with an apartment number to distinguish one from another. In this case, the case of a list, our apartment numbers begin at 0 instead of 1. And, as we saw with strings, we use square brackets to index into the list. Here's a version of the temperature program that uses a list. As you saw in Chapter 4, you create a list by putting its elements in square brackets separated by commas. And you access a list element by putting its index numbers in square brackets, as you see on line 6. Now, you may be thinking that's not much of an improvement. Yeah, we don't have the individual variables anymore, but line 6 is still as long. In fact, it's longer because we've had to add the square brackets. But remember, just as you can go through a string one character at a time with a for loop, you can do the same thing with lists. So instead of this big long expression, I'm going to set the sum to 0, and then let's say for each item in the day list, set the sum to sum plus the item. That's a lot shorter. And if I run the program, it still gives me the exact same result. One advantage of lists is now, if I have another week's worth of data, let's add some other numbers like 30, 31, 29, 29, 30, 30, and 32. I don't have to change this part of my program at all. It's exactly the same, it just goes through every single item in the list. I do have to change this line because now I have 14 numbers instead of 7. But to avoid even that retyping, I'll replace the 7 with the length of the day list. Then no matter how long or how short my day list is, I'll always get the correct answer. Let me go back to my original 7 entries, and you'll see it's working correctly. And this is the beauty of using lists with for loops. They work hand in glove with one another to make your life very easy when you have a lot of values that are all grouped together. Let's look at some more list operations, and we'll start by making a list of strings. In this little program where I set the words list to be the numbers 0 through 5 spelled out. Again, you access a list with square brackets. 0 is the first element, and 5 is the last element because there are 6 things in this list. That's the length of words. You can also use negative indices. Word sub negative 1 gives the last entry. Excuse me, let me type that correctly. Words negative 1 gives me 5. Words negative 2 gives me 4. If I go off the edge of the universe, such as words sub 6 or words sub negative 7, I'll get an index error because my index is out of range. Surprisingly, there's no find function for list, but there is an index, which returns the position if an item is found in the list. I can say words.index of the word 3, and that gives its position. If I say something that's not in the list,
it'll give me a value error. I can avoid that sort of error by using the in and not in operators. For example, is 2 in words? That's true. Is 14 not in words? That's also true. Let me show you this in operation in a program. I'm going to say number equals input of enter a number in word form. And then I can say if the number is in words, I'll print found at index words.index of number. I know I'll find it. I know I won't get an error because the number is in the list somewhere. Otherwise, if it's not in the word list, I don't want to generate an execution error. I want to have my own custom error saying, sorry, that is not in the list. Let's run this. And if I type in 3, found at index 3, run it again, and put in 7, and that's not in the list. We can take slices of arrays. We can take words starting at index 1 up to but not including 4. If I leave off the ending number, I get from the starting position to the end. The slice starts at position index 0. One really big difference between strings and lists are that lists are mutable. You can change elements of a list. For example, I can say words sub 1 equals uno. And now if I look at my words list, it has uno in position 1. I can change the slice to a slice of equal size. Let's take the words from 2 up to, but not including 4, and change them to the words dos and trace. And those two have changed. You can also change a slice to a different size. I can say words from 2 up to but not including 4 is going to be a list consisting of a single item, dos e trace, 2 and 3. I can go back and change it again and add more items. Let's take words from 2 to 3, which means only item number 2. And let's change it back to dos, trace, and add some extra stuff. And now I have extra stuff in the list starting at location 4. While I could use slices to delete part of a list by replacing the slice with an empty list, it's more readable to use delete, D-E-L. I can delete the items in the words list from 4 up to but not including 6. And I'm back to where I had it without the extra stuff. One more thing before we wrap up this video. Most of the times, arrays will have similar elements. As in our examples, all of the elements in the first program were all numbers, temperatures. In this example, all of the elements in the list were strings. That's normally the case, but it is possible to have elements of different data types, such as this. I can say person equals, and the first element of the list will be a string, the second will be an integer, and the third will be a float to represent and this represents a person's name, their age, and their weight in kilograms. It's also possible to have lists inside of lists, and that's a topic we'll get to in another video. Here are some other methods you can use with lists. First, let's make an empty list by putting 2 square brackets next to each other and show that it's empty. If we want to add a number to the list, we use append. If I say numbers.append 10, now there's a 10 in the list. Let's add another number. And append an 11 at the end of the list. Now there's 2 items, and we'll go with one more here. Notice that append changes the list. It does not create a new one. If you want to add more than one item at a time, you can use addition to add one list to another list. I can say numbers should refer to the old value of numbers plus the list 13, 14, 15. And now numbers has the numbers 10 through 15 in it. The pop method removes the last element of the list. If I say last entry equals numbers.pop, last entry will have the number 15 in it, and numbers no longer has it in there. You can also pop an entry in the middle of a list. Let's say mid-entry equals numbers.pop 2. If we look at mid-entry, it gets the 12, and numbers no longer has the 12 in it. Rather than use slices to insert elements into a list, you can use the insert method, giving the index number and the new value. I can say numbers.insert. At position 2, I want a 12. And at position 0, I'll put a 9. Insert inserts only one item at a time, unlike slices, where you can add as many items as you need.
Okay, that handles our laundry list of functions. Let's write a program that will ask users for numbers until they enter a negative number and store all those numbers in a list. We'll then find the average and print it, and then find out how many numbers are below the average, exactly average, and above average, and display that as well. First, the function to get the numbers. It's going to return a list of numbers as a result, so start with the empty list, and then set up the loop. We're not finished yet, and as long as we're not finished, we have to ask the user for some input. Enter a number or a negative to finish. Not great phrasing, but we can work on that later. If the number they entered is non-negative, then we can append it to our result list. Otherwise, we have a negative number, and we're finished, and we can return the result list. By the way, during these videos you may hear me say the word array instead of list. That's because the idea of a list is called an array in a lot of other programming languages, and I teach a couple of courses, so every once in a while I use their nomenclature of array rather than the Python nomenclature of a list. So bear with me, and whenever you hear array, think, oh, that's a Python list. Let's run this program and test it. We'll have a test list equals get numbers. Let's give it a 3, a 4, an 8, 7, and a 2, and a negative 1. And if we look at test list, there are our numbers. It's working great. Now we need the function to find the average of the numbers in the list. So we're going to calculate the average of some list of data. In this case, we'll set the sum to 0, and then for each item in the data list, we're going to add it on to the sum. To get the average, we need the number of items in the list, and that's the len function. We take the length of our data. If the number is equal to 0, which means they gave us an empty list to start with. We'll just set the average to 0. The average of an empty list is 0. That seems a good compromise. Otherwise, the average is the sum divided by the number of items. And we return the average. Let's test that. Let's make our test list, in this case, 10 plus 15 is 25 plus 11 is 36. Let's set average to be calc average of our test list. So it looks like that function is working pretty well. And now our main program. We're going to create a data list, which we'll get from getNumbers. We'll calculate the average, which is the calculated average of our data list. And then we'll print the average is, and let's use formatting here to make it look nice, to 3 decimal places, whatever the average is. Before we go further, let's test that to see if it works. And again, I forgot to invoke main, so let's do that and run again. If I take 10, 11, and 15 and then -1, the average is 12. Good. Now we need to go through the list again, counting the number of items in each category. The number of items above the average so far is 0, the number below is 0, and the number equal to the average is 0. For each item in the data list, if the item is greater than the average, then the number above becomes 1 greater. Otherwise, if the item is less than the average, the number below plus and becomes 1. If it's not greater or less, it must be equal, and so the number equal is incremented by 1. Finally, we need to display those results. We'll print number of items below average, the number below, the number of items equal to average, and pardon my typing errors here, is n equal, and the number of items above average will be n above. Let's clear the shell and run the program. This time let's do 10, 11, 12, and 15. End that. The average is 12. 2 of them are below. 1 is equal to the average, and 1 is above average. And there's our program that shows lists in action. In Python, it's possible to have lists inside of lists. These are called nested lists. Let's say we measure the minimum, average, and maximum temperature every day for a week. We can represent it as a nested list, as you see starting on line 8. Let's take a look at that nested list up close and personal. The main list has 7 elements, numbered 0 through 6, and each element is itself a list. If we were to print temps sub 2, we'd see this entire sublist printed out. Let's try it. Print temps sub 2. And there's our list inside the main list. Temps sub 2 is a list that has 3 elements, numbered 0 through 2. If we wanted to print the first element in the highlighted row, the 29.0, we'd print the element at index 0 in the row that's at index 2. Here's how you say that in Python. You print temp sub 2 to access the row, sub 0 to get to the first element in that row. And there's the 29. Here's a print statement that prints 3 other elements from the nested list. I've put numbers on lines 7 through 14 to help you figure out which row and which column is which. What do you think this print statement will print? Pause the video and figure it out before continuing. Did you get the right answer? Temp sub 6 sub 1 is row 6, column 1, 30.4. Temp sub 3 sub 2 is row 3, column 2, which is the 29.3. And temp sub 4 sub 0 accesses row 4 and element 0 inside that row, which prints the 24.6. Okay, now let's write a program to find the lowest minimum temperature and the highest maximum temperature for the week. The way we've laid out the data, you can think of each sublist as a row and each entry in the sublist as a column within that row. We'll start with a function called findMinimum that has two parameters, the nested list of data and the column whose minimum we want to find. This is more general than just finding the minimum of column 0. That way, if I wanted to find the lowest average temperature, I could use the same function. I'd just give it a different column number to process. Here's how this function is going to work. We'll start the minimum value as the entry in row 0 of the column we're looking at. We then look at the entries for every subsequent row. 30 is not less than the minimum value. 29 is not less than the minimum value. 25 is less, so that becomes our new minimum value. 24.6 is less than 25, so that becomes the new minimum value. 22.3 is even less, so it becomes the minimum value. 28.9 is not less than 22.3. And when the loop ends, our minimum value has the minimum entry from that column of elements. Let's translate that into Python code. We'll set our minimum value to the data in row 0 at the column we're interested in, and then we'll find the number of rows in the nested list. For row in range 1 through n, namely the rest of the rows, if the data at the given row and column is less than the minimum value, then the minimum value becomes the data point at that element. When the for loop is finished, we can return the minimum value. Now let's write and invoke the main function. We'll define main to set the lowest minimum to find the minimum of our temperatures data column 0. And we'll print the lowest minimum temperature is degrees Celsius dot format lowest min. Invoke main and run the program. The lowest minimum temperature is 22.3 degrees. And let's spell temperature correctly the next time we run it. To find the maximum value in the column, the logic is the same, only the names have changed. Let's copy and paste the minimum finder, change minimum to maximum. We start out with the maximum value being the first item in the column, and this time if the data in the row and column is greater than the maximum value, then the maximum value becomes the data element and we're going to return the maximum value. And in a similar fashion, we can say our highest maximum is find maximum from the temperatures nested list, this time column 2, which is the maximum temperature for the day. And the highest maximum temperature is degrees Celsius dot format highest max. Let's run the program. The lowest minimum is 22.3, the highest maximum is 31.6, And if we look at the original data, sure enough, this is our lowest minimum, and that's our highest maximum. And that's how you work with nested lists in Python. Here's a program much like the ones we've written before. It asks you for your age in years and then tells you about how many days old that is. In our getAge function, we have a loop that makes sure that you have an age that is greater than or equal to 0. Let's run this program and see that that works. If I say -2, it tells me age cannot be negative. If I put in 20, it gives me the answer. However, this program will die the great death if I enter a float, like 3.5, or if I enter something that's not an integer at all, like FIVE. Python provides a way to catch these errors, which are called exceptions. Python does this by using keywords try and except. The way it works: we put the keyword try before the code in question, the code that might get an error at runtime, and let's indent it. And then, if at any time a runtime error occurs during this block of code, Python will immediately jump to the except block instead of crashing the program and do whatever is in the except block. In this case, we'll print the message, please enter an integer that isn't negative. Now that we have done the try to catch runtime errors and an except to handle them, when we run the program, if I type 3.5, it'll ask me to enter an integer that isn't negative. If I type a word, it gives the same message. I'm still handling negative numbers properly, and I'm still handling positive numbers properly. Try and except let you handle conditions that would ordinarily crash your program. They're especially useful when dealing with files. Up to this point, we've put our data into arrays in the program, or we've asked the user to enter data at the keyboard. In this video, we're going to create a file that has data in it, and we'll write a program that reads that data, manipulates it, and then writes a new file to disk. Here's a file named actors.txt that has a partial list of actors and actresses who have won the Academy Award. It's sorted by first name. We want to write a program that reads that file, puts the names in the format last name, comma, first name, sorts them alphabetically by last name, and writes the results to a new file called actors_sorted.txt. First, we need an empty list for our result. Actors by last name equals the empty list. Next, we have to open the file by using the open function. We'll set our input file to be the result of calling open with the arguments actors.txt and r. The first argument to open is the path to the file. Since the file happens to be in the same directory that the program's in, we give the file name all by itself. If the file isn't in the same directory as your program, you'll need to specify an absolute or relative path. You can find out more about that at the links that are shown in the description of this video. The second argument tells what we want to do with the file. In this case, the R means we're opening the file so that we can read it. And the result in input file is a file handle. It's a Python object that's used to access the file's contents. By the way, if you try to open a file that doesn't exist, such as saying bad file equals open of no such file .txt for reading, you get a file not found error. And we'll talk about how to handle that kind of error in a subsequent video. Now that the file is open, we can use a for loop and read the file contents one line at a time. For line in input file, this for loop will read the file one line at a time and assign each line of input up to and including the new line character to the variable line. So if I were to print line in the loop and then run the program, you would see that everything looks as if it's double spaced, because print adds a new line and the line that we read in from the file still has the new line character at the end. That means we need to strip the rephrase. That means we need to strip the trailing white space to fix the problem. And I'll create a new variable just to make the difference clear. We'll say actor equals line.strip, which gets rid of the new line, and then let's print actor. And now we are getting the lines without that trailing new line. Let's comment out this print statement. It was just there for debugging. And add the code to split the name and put it together in last name first order and append that result to the list by last name. We'll say names equals actor.split. The new name is going to be names sub 1, which is the last name, plus a comma blank, plus names sub 0, which is the person's first name. Then we'll say actors by last name dot append new name. And to debug, let's print new name. Clear the shell and run. And it looks like I have an error because I forgot my plus sign here. Let's put the plus sign here to make it right. Clear the shell and run again. And now we have the names in last name, comma, first name order when we're out of the loop. After we've read the file, we close it by saying inputFile.close. It would close when we exited the program anyway, but this is a nice way to make sure that we have things cleaned up. Now I'm going to sort the file by last name and say actors by last name dot sort. The sort method for lists sorts in place. It does not create a brand new list. It changes the original. Now I need to open an output file for writing. The output file will be, again, open. We'll give the file name actorssorted.txt. And this time we'll say W because we want to write a file. If this file doesn't exist already, it'll be created. If it did already exist, it gets wiped out by the new one that you just specified, so you have been warned. Now we'll write a loop to go through the sorted list one person at a time and write it to the output file with the write method. For person in actors by last name, we'll call the output file's write method and give it the person plus a new line character. The write method requires a single string as its argument. Unlike print, you can't put as many arguments as you want separated by commas. It has to be a single string. Also, unlike print, it doesn't add a new line automatically. So if we want a new line in our file, we have to explicitly say so, and that's why we put the \n there, to explicitly put a new line into our output file. When you're writing an output file, it's ultra important that you close the file. This guarantees that any buffers the operating system is using to hold your file data will be written to the disk. There's our program. Let's put a message at the end that says print of file written as actors sorted.txt to give us some indication that the program has concluded. Let's clear the shell and run it. And if we go here and look at the actors sorted.txt, there are Academy Award winners sorted by last name. Let's modify the program that sorted the names of actors by last name and change it so that the user can specify the name of the input file to read from and the output file to write to. I've already put all of the program into a main function just for convenience. Our first change is going to be on line 9. Instead of opening actors.txt, I'm going to call getInputFile to ask the user. Here's that function. I'll define getInputFile to say file name equals input, enter input file name, and then input file equals open whatever that file name was for reading, and return the file handle. If I put in a valid file name, like actors.txt, everything works fine. But if I put in the name of an invalid file, instead of crashing the program, let's use try and accept. We'll set valid to false, and while not valid, I'm going to try getting the file name and opening it. And if there's an error, I'll print error opening file name. I also have to set valid to be true if it opens successfully, otherwise I have an infinite loop. Now let's run the program, and this time if I put in no such file.txt, non-existent.txt, it'll only continue if I put in actors.txt, and everything worked great. I'm going to do something similar for the output file. In this case, instead of always writing to actors_sorted.txt, I'll call a function called getOutputFile, which asks the user for the file name to write to. And since I don't know in advance what that's going to be, I'll just say file written here at the end. And now the function. It's going to be very similar to getInputFile. And I'm going to use try and catch to make sure that an invalid name doesn't crash my program. I'll set valid to false. While not valid, try, asking for a file name. This time my output file will be open of whatever name you gave me for writing. And if it was successful, everything's valid. Otherwise, let's give the error message that we would get from the operating system by saying exception as error. Print the error straight from the horse's mouth. And then return output file. Let's clear the shell and run the program. If I give a bad file name, it doesn't let me get by. I'll say actors.txt, which is a valid name. For a non-existent file name, I'll say non-existent/nofile.txt. And it says there's no such file or directory. If I say new sorted file.txt, which is a valid name, it wrote the file, and I can check that by opening new sorted file.txt, and sure enough that worked great. There's one more place for me to put a try and accept, and that's while I am writing the file. That could run into an error, let's say if I ran out of disk space, or if there was a bad sector on the disk and the program crashed because it couldn't write it properly. I'd like to be able to catch those errors as well. I'll do that by putting a try before the loop that writes my output, and an accept, exception as error, because I want to see the exact error that I got. I'll print error encountered, writing output file, and then I'll print the direct error message from the operating system. I'm going to add one more clause here. It's called the finally clause. The finally clause is executed whether the try succeeded or not. If the try succeeded, it'll go to the finally. If the exception happened, it'll still do the finally, and that's where I'm going to do my output file.close. This guarantees that whether I had an error or not, whatever did get written will be saved to disk. and I don't need that line anymore. I'd like to show you this error in action, but I don't know how to cause a hard disk error, and frankly I wouldn't want to, so you'll just have to take it on faith that this works. At any rate, that's how you use try and except with programs that read and write files to make sure they handle errors without crashing the program. Lists are great for things like the weekly or monthly temperatures, where you naturally index by the position in the list. What if we had a program that asks for the name of a country and then tells you the population of that country? Here's such a program using something called parallel lists. Each entry in the countries list has the population in the corresponding location in the population list. Here's our main program. We ask for a country, and if the country is in the countries list, we find its position using index, and then print its population by going into the corresponding entry in the population list. And if the country isn't in the countries list, then we simply say that we can't find the country. Let's run this program to see how it works. If I say Denmark and Greece, those work, and a country that's not in our list yet would be Croatia, and it can't find that country. There's nothing wrong with this program. But if we were to add a new country, say Croatia, in alphabetical order in our list here, we'd have to make sure that we put the population, 4,154,200, in the exact corresponding location in the population list. This is an error-prone operation, and it just feels awkward. Let's run the program again real quick. Denmark still has the correct population, and now Croatia shows up in our list. What we want is some data structure that makes this sort of thing easier. And that data structure is the Python dictionary. Let's think about using a real dictionary. Dictionaries aren't indexed by word. When you want the word atom defined, you don't look to see that it's word number 3472 and then look for definition number 3472. You look up the word atom by name, and right next to it is the definition. And this is exactly what a Python dictionary lets you do. Here's the start of a dictionary-based version of the countries and population program. On line 5, we have a dictionary defined. Instead of using square brackets, which are for lists, we use curly braces. Inside the curly braces, we give our keys, the things we want to index on, a colon, and the values for that index. So for the key Belgium, the value is 11,358,357. And for the key Greece, the value is 11,183,716. Let's go to the shell and do some experimenting. Although you use braces to define a dictionary, you still use square brackets when you index into it. Country pop of Denmark, I use square brackets, and country pop Greece. If I try to use as my index value a value that isn't in the dictionary, such as Croatia, I get a key error. I can avoid getting a key error by using the in or not in operators. I can ask, is Denmark in country pop? True. Is Croatia in country pop? False. So by checking first to see if the key is in the dictionary, I can avoid having key errors. Let's see how we have to change our main function. I've copied and pasted it from the previous program. First, the name of the list countries has to now become country pop, our dictionary. Because we're using a dictionary, we don't have to find an index number. The key is our index. And here, instead of saying population at our index, we go directly and say, look in the dictionary for the country in question, and that will retrieve the population. That's it. Let's run the program to see that it works. If I say Greece and Denmark and Croatia, we get the same results as before. So what has using a dictionary really bought us? The real thing that has bought us is the index and value are now in one data structure and not two. If I want to add Croatia now, I can go to the correct place, say Croatia as the key, colon, and then the value 4,154,200. This is just ever so much more convenient. Let's check to see that that works. Greece, Denmark, and now Croatia has been added to our list of countries. In addition to using square brackets to access a dictionary, you can also use the get method. I can say countrypop.get of Germany, and I can do countrypop.get of, let's say, Czechia, which we have not added yet. The latter call returns a special value none, which does not print out as anything. I can show you that. Let's do countrypop.get of Czechia is equal to none, and that's true. If you don't like having none as a value, you can give a second argument to get that gives an alternate value in case the key is not found. If I say countrypop.get Germany, 0, if Germany is found, it'll return its value, otherwise 0. Since Germany is in our country population dictionary, we get the value. If I do countrypop.get with Ghana, not in the dictionary, and 0, I get my alternate value of 0. One other important thing that we need to do is iterate through a dictionary. Here's one way to do it. I can say for country in countrypop, print country and countrypop of country. This for loop will go through all the keys in the dictionary and then print in the body of the loop, and there we have it. In this case, the countries happen to be in alphabetical order, but there's no guarantee of this. Keys are placed in the dictionary in a way that makes it easy for Python to access them. And if that happens to be the same as the order in which you entered them, well, that just happens to be good luck. Another way to iterate through a dictionary is with the items method, which gives you both the key and value, again, in whichever order the dictionary stores it. I can say for country, population, which returns both values, in countrypop.items, print country and population. Finally, let's look at a program that creates a dictionary from scratch. We're going to create an empty dictionary on line 6, set a finished flag to false, and as long as we're not finished, we're going to ask the user for a name. If the name is not the empty string, we'll then ask for an age, and this is how you enter something into a dictionary. You say people subname equals age, and you put the dictionary access on the left-hand side of the equal sign. If they did enter the empty string, we're finished. And then after we've entered all the names, we're going to use our items method again to get the names and ages and print them all out. Let's run that program. I'll put Joe as 29. Let's have Federico be 18. Let's have Nancy be 29. What happens if I put Joe in again and he's now 22 instead of 29? I mixed up his age with Nancy's. It's not an error. It just replaces the value for that key. And let's put in somebody named Albert, who's 17. All right, 29. And Kwa, who's 35, 36. I have a lot of people who are 29 years old, it would seem. And then when I press enter to quit, I get the names and ages. What if I want to make sure that I have the items in sorted order? Let's go to the shell to give you an example. I'll create a small dictionary here. Example. Let's put Jim and make him 26. Let's put in Alan and make him 37. And put in Barbara and make her 48 for her age. If I say name keys equals example.keys and look at that, it gives me back a special structure called dictionary keys that has only the keys from the dictionary. I can't use this in a for loop though unless I convert it to a list. So let's make name list to be the list form of example keys. And now if I look at name list, I've got Jim, Alan, and Barbara. I can sort it in place by saying namelist.sort. And now if I look at it, I have them in alphabetical order. And I can say for name in name list, print is years old dot format name example of name. And now I have them in alphabetical order. Let's modify our program to make use of this so that our people in the dictionary that we've created come out in alphabetical order. We'll put name list equals list of people.keys, and then we'll sort the name list. And then instead of using the items method, we're going to have to go back to the other way that we iterated through it. We'll have to say for name in name list, and instead of the age, we have to go into people of name. Let's save that and run it and see if it works. We'll have Federico, who's 19, Barbara, who's 20, Jorge, who's 35, Thomas, who's 22, and Steve, who's 47. And there they are in alphabetical order. Just as we worked with built-in functions before we wrote our own functions, we've been using objects throughout the course. For example, when we create a turtle, it's an object. When we want to tell the turtle to turn left, we use dot notation and say t.left 90, which tells the object t to use the left method with 90 as its argument. Strings are also objects. Let's create a string S and give it the contents A, B, C, D, E. Instead of having an uppercase function that we pass a string to, for example, new string equals upper of S, that's not how we do it. Instead, since S is an object, we say S dot upper. And now if we look at new string, we have it all in uppercase. Lists are also objects. Let's create a list. 1, 2, 7, 5, 3. And then we can tell the list to sort itself. And then we can print it. And it's sorted into order. Those are the kinds of objects that we've been working with already. Now it's time to write our own objects. It seems like nobody understands objects, but everyone understands toasters. So let's write a class to simulate a toaster as a Python object. First, what's the difference between a class and an object? You can think of a class as a template or blueprint for what an object should look like, and an object as the thing that you build from the blueprint. Or you can think of a class as a cookie cutter and the objects as the cookies you cut out using the cutter. The diagrams in the book that show what objects look like aren't standard, so I'm going to use a standard called Uniform Modeling Language to draw diagrams of what our classes look like. The class name is at the top of the diagram. By convention, class names always begin with an uppercase letter. By convention means that this is an informal, possibly unwritten rule for the way most people write and are expected to write Python. You can go against convention, but people will look at you funny if you do so. In the UML diagram, you then list the attributes an object of that class should have. Attributes are like variables. They describe the things that an object has. In this case, a toaster has a number of slots, a voltage, 110 in the US, 220 in Europe, the browning level, usually 1 to 6, the number of slices of bread currently in the toaster, and a Boolean that tells us whether the toaster is on or not. In a UML diagram, you give the data type of an attribute after the attribute name. The plus sign means that these are public attributes. Users can directly access or change them. Then you list the methods of the class, the things that an object can do. If we had a robotic toaster, it could turn on, turn off, insert slices of bread, pop them out, and set the browning levels. Again, the plus signs mean that these methods are available to anyone using our class, and you specify the data types of the parameters and the method return values. Let's start writing this class in a file called toaster.py. We start out with the name of the class toaster, and then a constructor method with the special name of __init__. It takes one argument called self. Again, this is by convention. Self stands for the object we are building or working with right now. In this method, we set all the default values for our attributes. The number of slots for our self is 2. We'll set the default voltage to be 110. The browning level we'll set to 1. The number of slices in the toaster is 0. And is on will be set to false. We can now create a toaster object. Let's create a toaster object called bread burner. And the way you create a new object is to use the class name, and that calls the constructor. And let's print bread burner and see what that looks like. And that's our result. Well, that's not very helpful. We'll find a way to improve on that later. For now, we can examine the object by accessing its attributes. Let's print number of slots, and we're going to say breadburner.nSlots, and that will access the number of slots property or attribute that belongs to the bread burner object. Similarly, we can say print voltage and then breadburner.voltage. Let's set the voltage to 220. We can say breadburner.voltage equals 220, so we can use it on the left-hand side of an equal sign to assign an attribute. And then let's print our new voltage, which will again access that attribute. Let's run this, and we have 2 slots, 110 before our change and 220 volts after the change. There's nothing inherently wrong with our constructor, but if we want a 4-slot 220 volt toaster, we have to manually reset the attributes. Instead, let's change our constructor and give it parameters so that we can create toasters with a particular voltage and number of slots. Since toasters should ship without bread in them, turned off, and the browning dial set to 1, we can keep that part in the constructor. So in this case, my constructor will now say, I want to have the self, I want to have a number of slots and a voltage when I build my toaster. The number of slots attribute that the object should have will be set equal to the number that I specified as my parameter, and the voltage of the object I am currently constructing will be the voltage that I specified in the parameter list. Now let's get rid of this preceding code. And this time I'm going to create two toasters. One of them will be a US toaster, and it'll be a toaster that has two slots at 110 volts. And I'm going to have a European toaster, which is a new toaster with four slots at 220 volts. Let's print the US toaster voltage just to make sure that it's correct. And let's also print the Euro toaster voltage to make sure that those were set properly by our constructor. And there's our 110 and 220. It's still unsatisfying to have to print all the fields ourselves. It would be nice to be able to say print US toaster and print Euro toaster and have the toaster object displayed as a string. We can tell Python how to convert an object to a string representation by supplying the underscore underscore str underscore underscore method, so that you don't have to see me typing for a long time. I've typed this beforehand and just pasted it in. Here's our underscore underscore str underscore underscore method. We create a string with placeholders and then use format to fill in all of the attributes of our object. And notice that we're using the if-else shortcut to tell whether the toaster is on or off, and we'll return that result. Now, when we run the program, when we say print US toaster, an object, in fact, a toaster object, will have to be converted to a string, and this method will be called. Similarly, when we print the Euro toaster object, the underscore underscore str underscore underscore method from the toaster class will be called, and we get some very nice output indeed rather than what we used to get. And now we don't have to print every attribute individually, although if we want to print one of them individually, it's still possible to do so. Finally, we need to write the remaining methods. The turn-on method sets the isOn attribute of the object we're currently working with to true. The turn-off method sets the isOn attribute of our object to false. Insert bread needs the number of slices to insert. This if statement makes sure that we don't overfill the toaster. The pop bread method makes sure that the toaster is on before we prop any bread, and no matter how much was in there, after we're done, there are no slices of bread in the toaster anymore. The set Browning method gets a level and checks to make sure that the level is in range before setting the Browning attribute of the current object. Here's how we call them. We create a toaster with two slots and 110 volts. We'll turn it on, and we'll insert bread, and then print the result. Let's run that. We have two slots, 110 volts, two slices at Browning level 1, and the toaster is currently on. Now wait a minute, you might be thinking to yourself, here's turn on. We called it and we gave no arguments, but here's turn on and it has one parameter. Similarly, when we called the insert bread method, we gave it one argument, the number 2. But here in insert bread, we have two parameters, self and insert. What's going on here? And the answer is self. Remember, self refers to the object currently under consideration. In these two statements, what's really happening is this. The object that we specify at the left of the period, at the left of the dot, becomes the argument that fills in the self parameter. When we called the insert bread method, the object that we're calling it with becomes self, and our other argument that's in the parentheses fills in the number of slices to insert into the toaster. Admittedly, this might seem slightly inconsistent, but that's the way the game is set up and we have to follow those rules. And that's the basics of creating and using objects. In the next video, we'll implement a class that lets us do operations with fractions.